problem with this kind of bubble.
Yeah.
Because I maybe need to raise for it to. Yeah, because that's why. Um,
Okay, I do have a loud voice, but can be heard online now. So yes, I'm Naomi McClure-Griffiths. I'm the session chair. This is FM2 Day 2, and we're moving into feedback today. So our first speaker is Deanne Fisher, How Galaxies Regulate Their Growth. Off we go.
All right. So we heard a bit yesterday from Adam and Rowan about kind of the small scale cluster, star cluster scale properties of feedback, and how we heard the story of how feedback, basically the early radiative feedback, will carve out regions like what we see here. And this is just a PowerPoint cartoon that summarizes about 1 million FANGS papers, where you have gas sort of falling in, and then it forms a bunch of stars, and then the biggest ones shine really bright. They impart all their momentum and their energy, and they carve that region out. And then what happens after that, and what we want to know in this talk, is how this process couples to the galaxy more broadly. And the important feature there is what the supernova do afterwards, like it was said yesterday. When you carve out that region, you sort of free up your path for the supernova to really impact the galaxy around it. And we want to know if that on kiloparsec scales, on galaxy scales, how this is impacting things. And the reason we want to know this is because there has been a problem for many years. Basically every galaxy evolution simulation tells us that you need something that slows down star formation and slows it down by a lot. Because if you don't have something like feedback in your simulation, your galaxies are like 100 times too massive, they don't have the right size, they don't have the right morphology. And so we want to understand if and how these processes couple. And so we have a sequence here. We're going to talk about it in kind of 2 parts. And it increases in star formation rate surface density. On the left, we have a disk galaxy, and there, the way the supernova feedback works, or what we're going to talk about, is how it sort of imparts and creates a turbulence in the system. We're going to see if in starburst galaxies, if that works well. And then we go to even higher star formation rate surface densities. That kind of turbulence is not enough, and what happens is you get enough supernova, you get a clustering effect of the supernova, and they have enough energy and momentum that they overcome the local gravity, and they send the gas out of the local potential into the galaxy around it, and then you're extremely effectively regulating mass growth, because the gas is just not in the galaxy to make new stars. So first we heard dynamical equilibrium brought up a couple times yesterday. And we're going to talk about it again. This is now what's become an old idea, where you have, it's based on very, very simple observations. Galaxies are not in runaway collapse. They exist, they have a thickness, and radially we understand that angular momentum is supporting them. But vertically, we know that there's a gravitation that's pushing them down. The gas wants to collapse, wants to push into a sort of hyper-thin system. But the fact that it's not, the fact that there's a thickness means something is pushing back out. And we know that this feedback exists. We know that supernovas are popping off. And so you can create a relationship between the pressure from gravity and the pressure that the feedback creates in turbulence. And you get a relationship between the star formation rate, surface density, and the pressure. In local spirals, this seems to work quite well. Jai Sun has done really great work with the FANGS data in the last few years, and I strongly urge you to go look at his papers, which shows these correlations, and you can sort of estimate the feedback efficiency, and everything is working quite well. Also, Cecilia Vicini has done similar work from a different angle, both coming to the same realization that you can explain the turbulence in these sort of local spirals with feedback. If we move to starburst galaxies, there's been a lot more questions there about whether the velocity dispersion, the turbulence, can be explained through this, and that's because people observe very high velocity dispersions. And so you can, from these same models, you can derive relationships that are quite intuitive in my feeling, where the velocity dispersion relates to things like the star formation rate, surface density, and the depletion time. And basically, if you have more star formation per gas in a patch, you're creating more energy and more momentum, and so you're churning up your turbulence. We see this kind of power law, where this is from the dynamo sample. Every point is a galaxy, and you see depletion time on the y-axis and velocity dispersion on the x, and you see there's a negative correlation. That is pretty consistent. The power law is pretty consistent with the expectation of the theory. The problem is the velocity dispersion is a lot higher than what is expected in the theory. When I took this to Eve Ostreicher and asked her what she thinks about it, Eve is a very good theorist, very smart, and it took her about a second to say your observations are wrong. And what she meant by that was that we were doing what everybody else was doing. The dynamo galaxies are somewhat far away, not super far away, but far enough that it made sense economically to measure the velocity dispersion with ionized gas. And Eve was saying, well, the ionized gas velocity dispersion is not what my theory predicts. And that theory is talking about the regulation of star formation. And so it's the regulation step is the cold gas cloud collapsing. And it said BCO, and I said, don't you think these are around the same? And she said, probably not. And so I said, great, I can test this. So if you're not familiar with a dynamo sample, basically, in one sentence, they are gas-rich, star-bursting disk galaxies. They have rotation, they have exponential surface brightness profiles, but here I'm showing you molecular gas surface density versus stellar mass surface density. Each point is like a sub-kiloparsec. And the blue is the dynamo, and the gray is FANGS. And basically, it just shows you they're more gas-rich. Dynamo galaxies have gas fractions of like 50%, star formation rates of like 20 to 40 solar mass per year. And so they're just star-bursting disk galaxies. And we can use these to first test the difference in the velocity dispersion. And so this shows velocity dispersion versus gas fraction. Blue is for ionized gas velocity dispersions, and red is for molecular gas. Those lines do not overlap. They do not intersect. They're very constant. When you look inside the dynamo galaxies where we have nice resolved measurements, the same factor is the same inside the galaxy as we see here. It does not depend on star formation rate, surface density. It does not really depend on location of the galaxy. It's the same one for different star formation rates. So this seems to be a universal offset that we see in a redshift 0 galaxy that's the same in a high redshift galaxy. So this means that we need to, that Eve was right, we do need to take this into account when we look at test models of what's driving the turbulence and what's regulating feedback. This work is on the archive today. That's how good I plan things. And we're showing molecular gas velocity dispersion versus star formation rate, surface density. Each blue point is from the dynamo galaxies as a kiloparsec sort of measurement. And the gray is Jai Sun's work in the FANGS galaxy. It's the same plot twice with two different theories overplotted on top of it. On the left side, those yellow lines are this theory by Mark Krumholtz that is the combination of feedback with an extra component that is meant to account for the high velocity dispersions that were previously reported. And that component is that Mark's argument was that you have these gravitationally unstable systems that have high gas fractions, and this creates a kind of mechanical movement through the galaxy. And that's all plausible, but then you assume in the theory that that with great efficiency translates to turbulence in the galaxy. And if that was the case, the dynamo sample, the blue points, should be between those yellow lines. It's two different sort of parameter sets of the yellow line. They are not. The transport model drastically overpredicts the velocity dispersions of molecular gas. When we look on the right, we see this kind of feedback-only model. The lines are from two different simulations, from Tigris and Silk. You can also overplot the analytic models from these where you get the same result. It agrees quite well. There's no tuning on our end for this. It just overlaps quite nicely. We can talk more about that difference between the velocity dispersion in the ionized gas and molecular gas. And there's pretty informative work done by Steffi Walsh and the Silk team. And this image over here on the left is one I think everybody has shown so far in this conference, where you have the ionized gas from a simulation and the molecular gas from simulation. And the Silk team do something that's really neat that you can do with simulations, where they go in and they turn on and off all the different feedback mechanisms. And when they go all the way off, and then they turn on the supernova, something happens. You get this ionization stratification of your ISM, where the ions react very efficiently to the supernova feedback, and the molecules do not. And this translates to velocity dispersion versus star formation rate, surface density that looks pretty much exactly like what we observed. Their ions are orange and the molecules are blue. The dark points are our data from Dynamo overplotted. And you see this completely recovers our observation. So pulling this all together, I think a few years ago, you would go to like a galaxy evolution conference and people would see these high dispersions and they would say, oh, you can't explain that with feedback. Feedback's wrong. But that's not what we're seeing now. What we're seeing now is even at high gas fractions, even in starburst galaxies that are disk galaxies, you can explain both the molecular gas velocity dispersion and the ionized gas velocity dispersion with the feedback models. In the molecular gas, you have this sort of dynamical equilibrium regulation happening, which sets the velocity dispersion. Our observations seem quite consistent with that. And then for the ionized gas, you get this extra kick that they more efficiently couple to the supernova feedback, and that seems to happen across a wide range of galaxies. Now we want to turn up the star formation rate, surface density much higher, and to talk about galactic winds, to talk about how you've regulated the high star formation rate in. So the blue and the gold points represent two galaxies where we have resolved out where the this sort of strong wind, like the biconical outflow kind of wind, is located. And what I want to point out is just how the environment changes. So you get in the lower star formation rate surface density areas, you do get sort of super bubbles, you get little fountains and things like this, but we're talking about the big, like M82 style bicones. For that, you need to be at really the tip top of the star formation rate surface density. And there, we know from observations of M82 and M253 that what starts happening is you start kicking out tons of material in both cold gas and warm gas. And the cold gas mass that you're pushing out of the disk there's more mass moving out of the disk through the outflow than you're making in stars in the disk. So this is becoming now the primary way that galaxies regulate their mass growth at the high star formation rates they're experiencing. Now, in the turbulent picture, I sort of presented this thing and said, we have it all figured out. When you talk about outflows, the story changes dramatically. There are really basic questions that we do not understand and we do not have answers to. And one of them is really just why is this cold gas there outside of galaxies? When you have a star formation driven wind, you expose 10 million Kelvin gas into your ISM. And for many, many years, it was thought that that must destroy all the cold gas. It must sort of ionize and heat up all that cold gas. But it's obviously there. We have observations from Alberto and from Adam and from many people that are showing that you get quite high mass loading in these systems. And now we're going to look into this with a task by looking at this James Webb data from M82 that comes from our illustrious organizer, Alberto Bellato, that's showing PAH emissions. And we're going to test an idea that came along a few years ago for why this gas exists. And this was proposed by Max Gronke and Pang-O. And so on the left is what happens in a traditional scenario. You have a cold gas, the red is your hot wind, and so that's your 10 million Kelvin gas is moving across. And it just quickly, through things like the Kelvin-Helmholtz instability, just quickly destroys your cloud, and that's what you see, the cloud going away. But they argued that if you incorporate fast cooling, that it's not unphysical, it's physically realistic fast cooling, the cloud can survive. And what happens is you get these structures that look like this, where you have this kind of bright bottom part, and then it gets kind of stretched out in this snaky thing. And with JWST, we have the image fidelity and we have the resolution that we can look and see, okay, does this exist? And are the properties of our clouds, are they consistent with what's being predicted in Max and simulation here? So we're just going to zoom in. These were the first images that came back from the JWST program. On the very center of M82 is NIRCam data of the 3.3 micron PAH feature. And what we're going to do is test specifically the breakout of disks. So you have gas leaving the plane of the disk. So in the olden days, it was thought that the cold gas would not survive that transition. And so we're going to see if it's there and if we see these little snaky things. And so we zoom in on it, we zoom in again, we have something like 2 parsec resolution. And you can see if you're as optimistically good eyesight as I have, you can see this kind of snaky thing going up that to my eyes looks a little bit like those simulations. We find several, these are just 4, we find more than these throughout the galaxy. Highlighted them there for you, and they're quite similar to what we see in the simulations. And so we can now use them to test this theory of cloud survival. So the way the theory works is basically just the Kelvin-Helmholtz instability. You have a hot fluid that's moving very fast across a colder fluid that is not moving as fast. They mix, and in that mix, in the traditional Kelvin-Helmholtz instability, you will sort of basically mix your cold gas with the hot gas and destroy the cold cloud. There is a time scale for that process to happen, and that is what's called cloud crushing time. It's over there. Chi-squared is a density parameter. Don't worry about that. The 2 things that we can measure are the size of the cloud and the differential velocity. JWST opens up this window to measuring the size of it. And that's what we get. You do it on the base there. That's the important part. And we find sizes that are of order 10 parsecs in size. So we're resolving it marginally. Yes, but we're resolving it. You can get the velocity difference, and this is an important part. And so you have this hot wind moving across, which we track. We say that's related to basically the X-ray wind velocity, something like 1,000 kilometers per second. And for the cold gas, we have something that's either ionized gas or CO kind of velocity, something in the range of around 500 kilometers. When we put all that in, we get cloud crushing times of something like 1 to a few million years. And then you compare that to the travel time. So if it takes longer to destroy your cloud than it does for it to travel to where it is, then that tells you the cloud could have possibly survived that trip. The travel time we find is about half a meg a year. So quite consistent with the expectations of the theory. This is really exciting. This theory has been around for a while, and now we can finally open the door to test it. It actually gets even more optimistic than this, because the velocity difference has to do with the gas that's around the cloud. And when we zoom out and look at the whole PAH image, the little tiny clouds are not just isolated in the middle of the hot X-ray wind. You can see these kind of plumes or channels of gas that are coming out. And so the cold, and when we look at where the X-rays are, they're where the PAHs are not. That makes sense. The X-rays are going to destroy the gas. And so the cold cloud is surrounded not necessarily by the hottest gas, by some sort of bath of colder gas. So that decreases your velocity difference. It lessens the impact of the Kelvin-Helmholtz instability and makes survival even more possible. So this is quite exciting. We sort of we're getting to a place, this is not conclusive at all, but what it's saying is we're getting to a place where we can start to understand the physical mechanisms for what's allowing the cold gas to survive. And the reason that's in a talk about what's regulating galaxy growth is that the cold gas is not necessarily going to escape the halo automatically. You don't really quench things that way. It's going to go up, a lot of it's going to come back down on the galaxy. And we have to understand the physical mechanisms that are governing that cold gas in its journey, because that's what's going to tell us how long it's going to take. And that time scale is the number we need to give the simulators to tell them how these outflows are actually regulating their growth. So the window is open. We need more observations now. And this is just a plug for the GECKOS sample. And it's building up systematically from main sequence. So GECKOS is a Muse large program. We also have ALMA data of edge-on galaxies. And it's chosen to systematically increase in specific star formation rates. And the reason that's quite useful for this is that we can now look at these different forms of gas leaving the edge of galaxies. And so I presented to you two separate sort of ways that feedback sort of regulates things. And now we can pull these together by studying the same properties of main sequence galaxies as we see in starburst-driven winds. So I'm quite optimistic about the future of this, and I think that we can make a lot of progress. So that's it. I'll just put I think I'm out of time. We'll just put my conclusions up.
Right, thanks. Very nice talk. When I see velocity dispersion versus star formation rate, and I think of whole galaxy models, where tumor Q tends to be regulated to a somewhat fixed value by lots of local instabilities, or if I look at observations of tumor Q, it's fairly uniform. In that case, the velocity dispersion depends on the column density for a given place in the galaxy, a given kappa. So when I see sigma versus star formation rate, I'm thinking column density versus star formation rate, which is the Kennicott-Schmidt law. So how much of that sigma that you plot there is from galactic scale processes, spiral waves, local instabilities? I'm not thinking of Krumholtz's accretion. I'm thinking of just normal local spiral galaxy, density wave kind of stirring versus feedback.
Yeah, so this is difficult to disentangle. We kind of there's a nonlinearity in our relationship that doesn't really track the expectation. If you were to just take like the Toomre formula and say, this is what's setting sigma dispersion, and you try to make a prediction, it doesn't really track it so well. You do get, they both are going in the positive relationship of, higher gas density, higher velocity dispersion, but it doesn't track it super well. It's close enough that if you want to be optimistic and make that bet, you can live with that. But doesn't do as well as it doesn't go straight through the data the way feedback does. Does that
Is that an unsatisfying answer for you, Bruce? Yes. Yeah. I'm always good for that.
Sorry if I missed this, but where does neutral gas lie between that sort of scaling that you showed for ions and molecules?
Yeah, so neutral gas would be nice to add to this. You know, as was pointed out yesterday, you have your cold and your warm neutral gas. I would love, it would be amazing to be able to put the cold neutral medium on that diagram, because that's the real thing that we want to see collapsing. But doing that with any present day telescope on an external galaxy, especially mine that are kind of far away, is quite impossible. We expect the warmer neutral gas is probably going to be a little bit elevated like the ions, but this is something to look into.
It's quite striking in all your plots. There's a factor of 2 offset between the molecular and ionized velocity dispersion. It's a wide range of physical parameters, many orders of magnitude. And you said across positions in the galaxy as well. Is there a simple explanation for that, or is it sort of TBD?
No, even the simulators that reproduce this, I mean, you can ask this to Steffi later today, but they as well say they know that it exists in the simulations, but they don't know why it is. There's no little analytic theory that says it could happen. I could make a hand-wavy argument of the ions are more easily excitable. So if you hit them both with the same sort of kinetic energy, they'll move farther. But no, that is needs to know.
Yeah. I feel that obviously simulations are quite complicated. It's got to be something more fundamental underlying this.
There's no easy explanation that I know of. Yeah.
Okay, we're out of time, I'm afraid. So let's thank you again. The next speaker is Ezekiel Trester, properties of the molecular and atomic gas of AGN mergers, ALMA, and VLC computers.
Okay, thank you very much, and good morning. Today I'm going to change a little bit the subject, but not so much. And we already talked a lot about feedback, but we were focusing so far in the stellar side of feedback. So I want to take you today to the sort of supermassive black hole growth, or the AGN side of feedback, and on the observational side as well. We know that feedback is complicated in general. The feedback from black hole growth is also very complicated. Here are just a few examples, both observationally from the work of Steph Junot, where we can see this sort of ionized gas outflowing, but also on the more, I would like to encourage you to read this review by Claudia Ciccone, where we can see that the feedback from supermassive black hole growth is both multi-phase and multi-scale, which of course makes it very complicated. And just to make it even more fun, I would like to focus today on the feedback that is happening on AGN that are happening in major galaxy mergers. And the reason for that is because that's where we expect the most significant feedback effects to take place. And even more specifically, I would like to focus on the last stages of the AGN in galaxy mergers. And the reason for that is because at least numerical simulations tell us that when the nuclear separations are less than about 10 kiloparsecs or so, okay, I didn't do that, thank you. When the nuclear separations are less than 10 kiloparsecs or so, that's when we expect the most significant effects, both for black hole growth, but also for the significant increase in the star formation rate. Now, of course, on the observational side, this is very complicated because you need both very high resolutions, but also because, as simulations also predict, these are the most obscure phases in the merger stage. So finding them has been very challenging, very difficult. And because of that, so far, we only have a few basically a handful, maybe a dozen, of confirmed systems, of confirmed dual AGNs, so basically nuclear separations less than 10 kiloparsecs and the two AGN active at the same time in the local universe. And by local universe, I mean redshifts less than 0.1, so about between 100 to 200 megaparsecs or so away from us. So as I said, we know about a dozen of these, what I will call confirmed dual AGNs so far. Most of these, and what I mean by confirmed is that they have X-ray observations confirming the presence of two independent AGN in these systems. And out of those, about 12 that we know so far, I'm going to focus today on about 4 of these systems that we have been studying through the years. These studies try to focus on all the phases of the gas. Basically, we are tracing both the neutral, ionized, and also the molecular gas. But basically, in the scheme of this meeting, I'm going to focus today about on the molecular phase, and in particular in ALMA studies of the molecular gases in these systems. So let me start with the first one. Okay, there you go. Markarian 739, I think, is a very nice, friendly galaxy system. You can see how smiley the galaxy is, and this is actually separated, at least in the line of sight, by about 3.5 kiloparsecs. Is at a redshift of 0.03, so about 100 megaparsecs away from us. And you can see, and basically, the ALMA observations, these are cycle 10 observations taken not so long ago. And you can see that, very interestingly, the gas is completely separated and appears to be basically almost undisturbed. Basically, we see basically emission that is and motions that are consistent with two rotating disks, which don't seem to see each other so far. Basically, the one we think that what is happening is that we have one of the galaxies, the one on the right, that is in front of us, and that is essentially a spiral galaxy, and the one behind is maybe an elliptical galaxy with a surrounding stellar disk at a distance of about with a radius of about 2 kiloparsecs, and that's the molecular gas that we see on the system, but there's no obvious interaction between them. So the next one in line is Markarian 463, which actually in the sky it has a similar nuclear separation. And also very similarly, we see two separate components also not interacting with each other. But in this case, more than an organized motion, we start to see something or some evidence of a potential influx into the nucleus. Let's say classical this than before. Moving on, we have another system, 6240, which is sort of the archetypical dual AGN, was one of the first ones discovered and one of the most studied. And we took observations also with ALMA at very high resolutions of this system. And in this case, what we find is that most of the gas, the vast majority of the molecular gas, is actually found in between the nuclei, and it seems to be sort of a filament connecting both of them. Also, very strikingly, very surprisingly, we find a very significant, relatively fast outflow at a velocity of about 500 kilometers per second, which, if you do a back of the envelope calculations, you get an outflow rate of about 4,000 solar masses per year. So this is very, very significant. This is how you really affect the evolution of the galaxy. Basically, about 10% of the molecular gas in the nucleus on the central region of the system is involved in this outflow. So this is very interesting. And finally, the last one we studied is the system UGC 4211, which we reported the discovery about a year and a half ago. And in this case, well, the nuclear separations is much smaller. I think this is still maybe the smallest separation confirmed dual AGN that we know so far. The nuclear separation is only about 200 parsecs. So this has been very challenging to discover. And in this case, we see very striking similarities with what we saw in 6240 before. Basically, we see that most of the gas, most of the molecular gas anyway, is in this sort of filament, and but it's starting to get into the nucleus and less in the filament or the bridge connecting them. Now, it's also very interesting that we don't see any CO in the southern nucleus, which is very interesting. It can be that the CO2 to 1 is still optically thick, or that most of the gas is ionized, and that's something that we need more lines or more molecular gas transitions to really determine. So, in a brief summary, what we are starting to see by taking these examples, and to first order, nuclear separation is a good tracer of the merger stage. Basically, as the two nuclei get closer and closer, it means that the two nuclei are starting to coalesce and eventually the black holes to merge. We start to see something that looks like what the theorists are telling us that we should see, where we start with two disks that are completely independent, completely separate, and relatively ordered, to basically start interacting with each other and finally start to get into the nuclei of the system. But I will agree that this is basically at this point just a stamp collection. It's only a four systems. We really want to increase the samples, and this has been very challenging. Basically, the last one, 4211, is at the limit of what we can do with Chandra. We are pushing the resolution. If we want to break these limits, we need to find alternative techniques. And in order to do that, now we have a new tool. Basically, ALMA has been critical. The outstanding spatial resolution of ALMA has been critical to reach nuclear separations of about hundreds of kiloparsecs to sort of break the kiloparsec limit. Not only that, but ALMA is particularly important because the selection is unaffected by obscuration. What we see with ALMA, and just a reminder, most of our systems are actually radio quiet, but what we actually see in this case is a very compact continuum emission peaking at about 100 to 200 gigahertz, that is coming from self-absorbed synchrotron radiation arising from each of the nuclei independently. Not only that, but very recently, it has been found that there's a very clear correlation between this continuum nuclear emission and the hard X-ray. So essentially, that means that the continuum emission is a great tracer of supermassive black hole growth or of AGN. And that's why we can use ALMA now to find some more larger number of samples at the smaller separations. And this is actually the PhD thesis of Macarena Droguet. And very quickly, I'm going to show you some examples. We have been targeting about a sample of about 30 sources, and these are just of the 3 of those, including one that, if we can confirm, it will be a nuclear separation of only 100 parsecs. So just to finish, a little bit for the future, and in the theme of this focus meeting, the future looks very bright. In the near future, we will have SK8, which will be an amazing complement to ALMA. With SKA, we can extend the ALMA coverage to lower frequencies and therefore confirm basically the alternative here, instead of having those double nuclei, is to have jet nodes. And with combining ALMA and SKA observations, we can actually confirm that these are actually dual AGN system. And of course, about a decade from now, and NGA-BLA will be absolutely critical for that. We will be able to reach sort of parsec scale separation, which is very exciting because that's when we start to see the progenitor of the gravitational waves events that we are going to start to see with LISA. So hopefully, I would like to leave you with my conclusion, but hopefully you can see that now we are starting to explore the ultimate frontier in our senses of black hole growth. We are starting to see what the gas is doing during a galaxy merger in the last stages of the merger. And hopefully in the near future, we will actually be able to study the last stages right before coalescence of the supermassive black holes, and eventually the parent population of the gravitational wave events that we are going to detect with LISA. So thank you very much.
Before we take questions, is Maria Vittori?
More time for questions then.
Thank you for a great talk, Ezequiel. So I've seen this before in the, and I just don't quite understand what is the mechanism for the millimeter emission. So can you explain it in a few words?
Well, I don't think we know for sure yet, but what we think is happening is that this is coronal emission and essentially is associated with soft-absorbed synchrotron, which of course requires strong magnetic fields as well. So this is so far the best scenario that we have for it. Now, I'm not going to claim it's the only one.
So when you say self-absorbed, you mean it's self-absorbed at longer wavelengths. So
Yes.
you don't see it peak there, but you see it peak a millimeter wave.
That's very important. And that's why I thank you very much for the question, because I didn't have time to get into that. But that's why we can combine BLA and in the future SKA observations, because essentially when we combine the observations of sort of tens of gigahertz, sort of 15 gigahertz, with the 100 gigahertz, that's when you can separate the coronal emission from, for example, jet nodes, which you expect to have a rise in a spectra, for example.
Okay. And the electron densities implied by these are very, very high, presumably.
Absolutely, yes. And just a little, and we are starting to do that also with the VLBA. And actually, we did get observations of one of these sources last night, but I'm not going to talk about them today because.
Another question? Fortunately, we're just about out of time, so thank you very
Excellent.
much.
Thank you.
Okay, so the next speaker who was on the program is not here, so we're going to move on to Evige Corbelli. Star formation drivers in the local universe.
Okay, good morning, everyone. I'd like to start with the usual thanks to the organizer for this very nice conference on the interstellar medium. But my second thanks goes to the icon of this conference here that I placed here, because in this icon there is a very nice galaxy that is M33, which I like very much, and I dedicate part of this talk to the interstellar medium M33, showing indeed the icon of this very interesting conference. Okay. So here are my collaborators for this talk, and let me start with the first slide, which is a kind of a summary of the many effort that the scientific community has put on understanding the driver of star formation, resolving single galaxies. So when you have just 1 point, sorry, when you just have consider just a galaxy like a whole, so integrated quantities, life is much simple, but life gets more complicated if you try to analyze individual region in galaxies. You have papers with different indicators of you know, who wins the best correlation with star formation, or you know, what kind of variable you want to analyze in a galaxy. But you have a lot more of information to take into account. And you know, I'm showing here at the bottom an example, a few examples of surveys of local galaxies where people resolve mostly kiloparsec scale region and analyze region of star formation which are above 1 solar masses per square parsec per giga-years. So you can recognize some of your favorite here. And I like to focus a little bit on this survey that involves also my my collaborator. And to the next slide, I'm going to show you just a piece of science that came out from the AlmaQuest extended sample that Sarah Ellison led. And if you notice in my previous slide, I was reporting plots of star formation versus the dynamical pressure, equilibrium pressure, PDE, that is defined in this slide down here for those of you who don't know what PDE is. PDE is the sum of two terms, and it's the usual weight of the interstellar medium, the compression of the interstellar medium that feels due to the stars, to the gas, and in these also the dispersion plays a role. And this is the dynamical pressure as it is formulated by Yves Stryker and other people. Okay, so if we take this definition into account and we do an analysis of what is driving star formation in the ALMA-QUEST sample, what you find is that there is a clear peak here to the PDE. So PDE seems to be the main driver of star formation. And while all the other, like the molecular hydrogen, the stellar surface density, and any other combination seems to have a much lower relative importance in the process of star formation. So, and what I would like to underline here are also another result from the same paper. So not only PDE is a superior predictor for star formation, but also there seems to be deviations from the Stryker and Kim model, which this model implies that the feedback is what regulates also the pressure, and the star formation are in a sort of local equilibrium. So turbulence is driven essentially by the local star formation process. And there seems to be in the ALMA-QUEST sample a deviation from this relation that is the red line, the dashed red line here. And the deviation, if you can see, the distribution of the pixels flattens towards the high pressure regions. And the conclusion of this paper is that the deviation in this particular sample are due to starburst region in galaxies, so starburst galaxy, which lie above the main sequence. So this starburst galaxy deviate from the relation because there are no local sources of turbulence, which is due to the inflow of gas to accretion and merger that dominate of the local feedback. So that's one of the main results of this paper that I would like to underline. So now, going back to the drivers of star formation, I like to analyze a bit more in detail why is PDE coming out as, with such a strong peak. So for doing that, I like to focus on my favorite galaxies, which is M33. And but first, I'd like to underline also that in general, we'd like to extend the ALMA-QUEST sample, involving also more hydrogen, atomic hydrogen dominated galaxy, because the ALMA-QUEST sample represents a population of galaxy very rich in molecular gas. So we like to extend this sample by looking also to more atomic gas dominated galaxy. And for doing that, we are both doing the Maluca survey, which is the Manga Lomas disk hunt for CO with PI of Marco Grossi in Brazil. And the other point I'd like to emphasize that what about doing a similar analysis to what has been done for the ALMA-QUEST sample by taking a galaxy where we have a full database? So no assumption, and just a look point by point to all the quantities. So for M33, we have the dispersion of the CO, of the H1, of the stars. We have the dust map. We have everything. So why not looking at M33? Even though M33, I want to underline, it's a later type galaxy compared to the ALMA-QUEST sample. So don't take, the results of M33 as, an example for the whole ALMA-QUEST sample. So 4 questions I'm trying to answer, and the questions are, first of all, is M33 a disturbed galaxy? Second, what is driving star formation across M33? Are star formation and turbulence self-regulated, the local process in this galaxy? And the last question is atomic gas relevant for star formation in this galaxy? Okay, about the interaction for with M31, there's been a recent paper by Andy Burkett and myself, a numerical simulation using the Gaia DRT survey. And our conclusion is that there is no way that we can reproduce the warp of M33, the H1 clouds, by just making M33 passing through M31. So M33, it's an undisturbed galaxy from the point of view, it's not tidally disturbed. This is a result. If you want to hear more, you can come to Division H. I gave a talk just on this, but you keep in mind that there are no parameter compatible with Gaia data that can explain the H1 warp of this galaxy. So our conclusion is that the H1 warp and the H1 cloud in the outskirts of M33 are due to a recent accretion from the filament, from the local filament into this galaxy. So that's for the first question. Now, going on to the second question, the driver of the star formation. I am showing here the results of the random forest, as I did sketch in the first slide, looking to several quantity across the disk of M33, that some of you have talked already, like pressure, but not only the dynamical equilibrium pressure, but also the hydrostatic pressure, which is different, from the dynamical pressure equilibrium, because if you take into account the scale height variation across the disk of this galaxy, and the fact that this galaxy is dominated by stars only in the inner disk, but then it's dominated by gas in the outer part of the disk, what you find? Well, you find a very good correlation with the hydrodynamical pressure, the hydrostatical pressure, so more than with the PDE. And in the outer part of the galaxy, instead, the best correlation is established with the dust. So dust is playing a crucial role in the second part of the disk, in the outer part of the disk of M33, to drive the star formation. These are the results I'm showing here are results at 250 parsecs, so lower resolution than what other surveys have done. And I have also, result, of course, through a range of resolution that I could have shown if I had more time. Okay, then one warning is that making assumption on H1, on the dispersion of the gas and also on the H1 content of galaxy often makes a relation more tight. I am showing you an example, for example, for here. If you look to the PDE, for example, here you see the real scattered with non-assumption, but if you make assumption on it, the usual assumption that they are done on the H1 content and the velocity dispersion, you get a much tighter relation. So if you run the random forest with the assumption, you get a much more peaked relation on one indicator rather than what in reality data are telling you. The second thing is mixing the inner region with the outer region. The process may be very different. And so if you mix the two regions, you may get a relation which is very, very similar to what the Oestreicher and Kim model predicts. But then if you subdivide the galaxy into the inner region and to the outer region, you get two different slopes, which means that feedback is not really self-regulating star formation. So it's turbulence dominated this galaxy, as I am saying in my next slide. So inside the co-rotation radius, which means in the inner disk, the hydrostatic pressure dominated by stellar gravity compresses the INSM and triggers molecule formation. But however, those clumps, they are collected through the arms, the weak arms of M33 in the inner region, are making giant molecular clouds which have they disperse in 14 million years, as I show here. And those time scale has been confirmed by the recent James Webb Space Telescope imaging of star-forming region M33, where you can see the protostar, they are really clustering around these giant molecular clouds. And these young stellar object confirmed by the James Webb picture confirm also all the identified young stellar clusters previously in this galaxy of type B, C, and D, which means everything associated with either optical emission or CO in this galaxy. So these young stellar clusters are a unique sample through the literature of the galaxy, outside of the Milky Way and the Magellanic Clouds. So this is about the inner disk of M33, and you can see also a simulation of this inner disk in the panel here made by Dobbs a few years ago. The giant molecular clouds in the inner disk are highly turbulent and form a log normal PDF, but this turbulence is not only linked to the local feedback, but there are perhaps other sources that make the slope deviate from the predicted slope of a Stryker and Kim model. So my last slide, and I have done, is that the role of atomic gas. Atomic gas plays a major role, especially in the outer regions, that it's dominated completely by the atomic gas, and where thermal and gravitational instability are forming dense filaments, where the dust and metals favor cooling and make, the gas collapse for star formation. And I want just to show you here the main sequence of M33, where you can see the H1 rich region like they sit above the main sequence, which is also confirmed by the analysis of 6 to 8 by another local galaxy. So I'd like to emphasize at the last point the fact that, of course, we need more survey like the NGVLA and the SKA to confirm the picture of M33 by sampling in the inner and outer region, especially the star formation across the disk of local galaxies as well. Thank you.
Thank you. Time for just one quick question. Oh, yep. It's coming around, Adam. Oh, no, he was pointing to you, I think.
Oh, I see.
Yeah.
I'm sorry. So on the dust is interesting. Do you think it's a dust to gas ratio variation in the outer part? What do you think the physical mechanism that's causing the predominant correlation with dust column in the outer parts are?
Yeah, I think that first of all, the dust is linked to metallicity, and so metallicity is cooling the gas more. So where is the dust? There are a lot more metals, so they are in homogeneity in the second in the disk of M33. So cooling is surely what it does. One thing. Second of all, of course, dust is essential for the formation of H2 molecules. So you need dust, and again, if the metal and the dust are not uniformly mixed in the other disk, that's what makes the difference. Okay.
Do you have a sense of, does the dust look different than the H1 within a given ring? Like, is there a distinction? Yeah. Is it a primarily radial effect, or do you have a sense of like, is it?
No, it varies azimutally. Azimutally varies a lot. Yes, the dust, that's actually the dust map that we have. If you see the dust map, it's slightly more flatter than what you see through the density of the intensity field. Like if you look to the intensity of 250 micron, for example, the dust mass is flatter. However, it's not as flat as the H1. H1 is even more flatter if you talk radially. But azimutally, both the dust and the H1 have quite these long filaments behavior that are due to the gravitational instability in the disk. That's what comes out also from the simulation. If you just forget about feedback and you run the simulation with the parameters of M33, you see this filament forming that is quite typical for the outer disk of M33 with little feedback or nothing.
Okay, I think we better wrap up there. So thank you very much. So our next speaker is Loreto Barcos Munoz. Sorry.
All right, thank you, everybody. My name is Loreto Barcos Munoz. Sorry. Hi, everybody. I'm Loreto Barcos Munoz, and I'm a staff at NRAO in Charlottesville, Virginia. I work for ALMA, so if you have questions, I'm not going to talk about ALMA technical ALMA stuff, but ALMA observations. So if you want to talk about ALMA afterwards, you can also approach me. All right, advance. Great, thank you. All right, so yesterday, yesterday we heard about a little bit about luminous infrared galaxies from Petro. And just as a reminder, these are very luminous infrared galaxies. They are defined by their infrared luminosity. Above 10 to the 11, they are LIRGs, and above 10 to the 12, they are ULIRGs, ultra-luminous infrared galaxies. In this plot here in the SED, I'm showing different SEDs for normal galaxies in the bottom and going up in infrared luminosity. And you can see how you go up in infrared luminosity and most of the optical light gets suppressed and everything else goes up into the infrared. We heard about this yesterday also. Deb was talking about how UV radiation gets absorbed by the dust and re-emitted in the infrared. And so the high infrared luminosity in these galaxies tell you that they are also very star-forming systems. To have a star formation, they have to have a lot of gas, so they are gas-rich. They are very dust-rich. They are very luminous in the infrared. And in general, they look like this. They are interacting systems, although we do find isolated ULIRGs and LIRGs. But these interactions actually allow the gas to be funneled towards the center. And at the end, we find most of the emission coming in from very compact regions. So today, I want to talk about just a few of them. It's a small sample of them that I targeted ALMA observations. As I mentioned before, these systems are compact and dusty, so we need rate interferometers to observe them. We need very high angular resolution, which can get with ALMA and VLA. And today I'm going to talk about these 6 galaxies where we observe CO 1 to 0 observations at high angular resolution, mostly matching previous VLA observations. You see them, I mean, I have one ULIRG and the most luminous, these were selected to be the most luminous, closest to us, with no CO 1 to 0 observations that were also in my previous survey for the VLA. This is a sample. This is the same 6 galaxies now shown in the continuum emission at 33 gigahertz. This is part of my thesis where we observed 22 of them. These are the 6 that were observable with ALMA with decent beam elongation. And I'm highlighting here just the scale sizes. For some of them, it's tiny, so 60 parsecs or so. And for others, we have 700 parsecs or so. Mostly, these resolutions were done so that we could recover at least 50% of all the light and recover the sizes. If you squint your eyes, you can see a red contour. That is the half-light size for these systems. Notice 3CQ35, that is unresolved at 50 parsecs. All right, next. So when we observe them with the CO, one thing, 33 gigahertz is used as a star formation ray tracer in this case. We know the radio IR correlation also holds at 33 gigahertz. This is, of course, still an assumption, and I'll talk about that a little bit later. All right, and this is how their maps, look like. The CO is concentrated in some of them in the center. Some of them show more extended emission. Don't be fooled by these outer contours here, that's noise, but basically we observe CO in these systems. All right, so the first thing is we have gas, we have a star formation, we have sizes for these systems. I took the core data for this, so the half-light size, I measure the star formation rate from there and the molecular gas. And if we place them in the Koenig-Schmidt, they all lie here in the very high regime with million years of depletion timescales, which sounds too much. I mean, too fast. And for comparison, I took a screenshot yesterday of Fabian's high Z quasars, and I put them there. So these are the high-Z quasars that Fabian showed yesterday, and I'm finding in the nuclei of these galaxies are comparable to those. So, but the thing is that they are forming a lot of stars. So are they forming their stars at their maximum capacity? And Deb talked about this yesterday, and I need to talk to you about radiation pressure on dust. So these systems are very dusty, as I mentioned, very compact. So the main mechanism that it's probably acting on feedback here is feedback on radiation pressure feedback, so radiation pressure on dust. Deb did a very good job yesterday about showing this, and basically it's radiation pressure acting against gravity. And here I'm showing you a plot from Yijing Song's paper. She's currently an ISO Alma Fellow. She did this work while she was a graduate student at UVA. And here you see the luminosity surface density that you can derive at 33 gigahertz with versus size. You find different models. This is again based on radiation pressure on dust, assuming feedback and no feedback for the two different lines, and different gas fractions. The one up top is assuming a dispersion of 300 kilometers per second, but the other three at 200 kilometers per second. And sorry, I missed this, but there are other mechanisms that could be affecting these systems, not just radiation pressure on dust. But we think, of course, I mean, supernovae explosions are important, but cosmic rays, stellar winds, expanding H2 regions are all play a role in this system. And here I'm showing you, these are the 5 of the 6 galaxies that I showed earlier. And when I measured gas fractions, and this is just using dynamical masses and CO conversion factor to get the gas, I'm getting that for these galaxies, they show very high gas fractions in the core. Some of them have a little bit less. But however, for all of them, it seems that they are not at their maximum capacity. They are not above this line. If they are above this line, we need to invoke an AGN, for example, or something is wrong with our assumption of radiation pressure being the main feedback mechanism. All right, so the thing is that if they are above this Eddington limit, they should show, for example, outflows. They are not. I mentioned they were not. However, they are full of outflows. So something is happening with the theory here when we study feedback. So for example, here, Tusuki 96 has very strong wings. This galaxy has a very compact outflowing gas. 3Ck35, the one that is the most compact, shows a very strong CO molecular gas, but also warm molecular gas along the minor axis. And then we have these other galaxies where it shows, this is CO 221, and it shows some rotation, but also in the dispersion, you see that it's highest in this direction. And with JWST, this is warm H2, we're finding a biconical outflow. And these, the previous one were just the ones that I'm just showing right now, but there are plenty of outflows in the literature from these sources. I'm not gonna explain every single one of them, but just to show you, and they keep going. One thing that I wanna highlight here is this one where it shows the outflowing material as well. It shows a jet at 5 gigahertz. This is relevant for SKA and NGVLA frequencies. The other one that I wanna highlight is ISO 320, which we heard from Petro yesterday. This is at 5 parsec resolution, and they are finding, Mark is finding these collimated outflowing material in HCN. But today I want to talk also about this galaxy that it's not part of the 5 that I showed for the Eddington limit. This is BB340. It's a very gorgeous galaxy, as you see. It's an edge-on galaxy with a face-on. It's an early stage merger. It has a decent star formation rate. And when we observe this with VLA, JWST, and TEC, we observe a multi-phase outflowing material. When we observe with ALMA, there's no molecular gas. There is coronal emission along the minor axis in red here. This is about 3 parsecs inside. And the radio emission at 6 gigahertz shows a bending S-shaped radio jet. And again, ALMA here, I'm used to having ALMA being the highlight of things, right? In this case, ALMA is showing us no molecular gas in this jet. This jet is also processing. This is work done by Justin Cater, who is about to resubmit this work in Science. When we, and so we know that this is the nature, the powering source of this source is of course an AGN. You cannot have starburst, coronal emission with a starburst like this. And so, but this is one source. And what is powering these sources in general, right? So I talked about 3CQ35 being the one that is the most compact. When we go, this is work that started with Maynor Rodriguez, who is an undergraduate at the Universidad de San Carlos de Guatemala. He was part of the SENCA Bridge program, so this is part of the ODE prize that we heard yesterday. And so we observed this 3CQ35 with very, very high angular resolution in band 6. This is 30 milliarc seconds. This is band 3 at 0.1 arc second, and I showed the 33 gigahertz continuum at 0.1 arc second where it was unresolved. And when you go to 30 milliarc seconds, this thing breaks down into a central compact source and some semi-ring. And when we get, this is in-band spectral indices, we get that the core seems to be dominated by synchrotron emission, probably from the coronal emission that we were just talking about, Ezekiel was talking about. And then maybe these knots here are dust dominated. And so I want to just finalize with the exquisite, the future is very bright. The sensitivity of the future telescopes will allow us to detect these jets. The resolution is going to allow us to go from single points to resolve structures. And we can do this now. 30 milliarc seconds you cannot achieve right now at multi-wavelengths, but we will be able to do it with SKA and NGVLA. And plus, they are both going to contribute, along with ALMA, to the millimeter CO emission in these galaxies at exquisite sensitivity and angular resolution. So complete coverage of the sky at high angular resolution and sensitivity at centimeter and millimeter wavelengths equals a very, very happy radio astronomer. So thank you.
Time for a quick question or two.
I guess you don't have JWST data for all of these, but have you tried to use diagnostic tools to determine sort of whether there's any sort of young AGN in some of these systems that you've looked at?
Yeah, well, so they, I'm part of the GOES collaboration. So they have ERS, so early release science for 4 targets. The main thing, the trend seems to be trying to detect coronal lines, but not all the AGNs have coronal lines. But also using some sort of BPT diagrams to determine the presence of AGN. So there is a large program led by Lee Armis that we observed. It's a cycle 2 program where they are targeting all the ULERGs in the GOES collaboration, in the GOES sample. And that would be one of the things that we will do. But let me tell you that actually the coronal emission, millimeter coronal emission that Ezekiel was talking about seems to be promising to do this because you can get very high angular resolution, higher than JWST, and that allows you to, in these systems that are very compact, allows you to at least try to separate the circumnuclear starburst, you know, that you have from the central AGN. While JWST, you have everything combined. So.
I'm afraid we're actually out of time. So thank you very much. And our next speaker is Filippo Macagno.
Okay. Okay. Hello, everybody, and I would like to thank the organizers to let me give you the opportunity to speak about this some nearby AGN. And the title of my talk is Multi-Phase and Multi-Wavelength, the Feeding and Feedback AGN Cycle Revealed by Sensitive Observations of the ISM. And this is not only my result, but is the part of the work of also other many people that I acknowledge here, as well as the two ARCs that paid for my salary for the last 7 years. So, this button. Okay, so Ezekiel already explained today that AGN feeding and feedback is complex and it's multi-phase. And here you see a simulation where you see the jets coming out of the circumnuclear regions, and usually the jets, but also radiative winds have a strong impact on the ISM. They can heat it and shock it and eventually deplete the galaxies of their gas. But also what happens is that part of this gas may cool down again and fuel the AGN, and this can happen recursively. So we want to study this phenomena observationally, and mainly with the cold gas, and I'm gonna talk about H1 and CO. So in H1, we were so far limited with by the resolution and sensitivity of the old generation of interferometers, and so we have many examples where we can identify AGN feeding or feedback, for example, through absorption lines. And also we can, I really cannot speak in the microphone, I'm sorry. And also we can, so we were limited in the circumnuclear regions by the low resolution, and so we could only study through absorption. And here you see two examples of an outflow, so blue shifted lines, or an inflow, a red shifted line, for example, or by the sensitivity, but we could still identify, for example, positive feedbacks on the circumgalactic scales. And here you have two examples of like the Minkowski object and Centaurus A. Now, another example that I like, because from 2013, we could also combine H1 with, for example, the CO information from ALMA. And one example is the Younger radio AGN Parks 1718-649, where you see this doublet of absorption against a very small radio jets, only 2 parsecs, which also indicates that this source is very young, and so the AGN activity just began. So this could not be explained with rotation, and we thought that there must have been cold gas clouds not rotating nearby the AGN. So this gave us the opportunity to study with Symphony, the warm H2, and with ALMA through the CO221. And we could identify this circumnuclear disk of around 200 parsecs, where you can see with a position velocity GA diagram across the major axis, that right in the center, we have a feature that cannot be explained by rotation. And now this feature is seen in the warm H2 in emission, and in the CO221 in absorption, as you can see from this spectrum. And this allowed us to locate these clouds within the innermost 75 parsecs, which is the resolution given by Symphony, because since we have a kinematical correspondence of the two molecular gas phases, and we see it in absorption, this must be in front of our small radio source. And as you can see it by the emission, this feature is only limited in the innermost regions. Now, we can do this thanks to the new telescopes and all the ongoing surveys in H1, we can access the column densities that we were seeing in absorption with emission. And this, we are talking about column densities between 10 to the 18 and 10 to the 19. So this is the project that I'm carrying on, where you can see, which is called Magnific. Since every project must have an acronym, I have a Magnific one. You see that I selected the galaxies between 20 and 60 megaparsecs plus Centaurus A, because we can really investigate with in emission this gas that is the typical gas that is identified in feeding and feedback. And here you see other previous studies in the H1. So we're really accessing a new parameter space where we can study the cold gas from the circumnuclear scales to the circumgalactic scales. So here you see the sample that I'm collecting from different Meerkat larger programs and also open time. And one of the galaxies I point out is NGC 5643, which is also part of FANGS, and you may have seen Karina's poster yesterday. So today I'm gonna talk about NGC 3100, and of course, we also looked at it with the compact array before doing this with Meerkat, so we had an idea of the H1 that was in the field, and this radio AGN that you see here, the jets, has a circumnuclear disk identified by several lines of DCO emission. Now, what we saw with ARCA was this cloud that is dark because we see we don't see any stars below down to a surface brightness of 27 magnitude per second. So what we hypothesized is that this cloud is probably fueling this AGN, but you see we don't have a great connection between the two. And of course, we identified H1 in absorption in the center against the radio jet, and a model of the kinematics shows that most of the absorption traces the circumnuclear disk seen in CO, but we also see another feature. Now with Meerkat, we have a game changer because this is 25 hours with Meerkat, and the contours you see different resolutions from 90 arcseconds in yellow to 7 arcseconds in red. And you see also that at 7 arcsecond, we can access column densities below 10 to the 20. Now, we revealed that NGC 3100 that is in the center here is part of a very H1 rich group where we identify several clouds that have no optical counterpart, but also several low surface brightness galaxies, and some of these are probably also UDGs. So lots of science that can be done in this field already. Now let's focus with the AGN. We go down in the center here, and we see that the darker cloud has become a very long filament, and clearly probably the remnant of the interactions between all these galaxies. And this filament, we can track it down to the innermost regions of the galaxy. And I'm gonna prove you this with this position velocity diagram across the filament. And you see that we can go down to the real center, where then we see the absorption line. And again, the absorption line has these two redshifted clouds that with ARCA were barely visible. Now, what is interesting is to combine the H1 information with the CO120, and in the CO120, we had this blue shifted cloud close to the circumnuclear disk, and in red contours, you see the H1 in two channel maps. And what is interesting is that, again, we have the filament falling onto the galaxy and likely fueling the circumnuclear disk. And we can trace this from the circumgalactic scale to the innermost regions. Now, let's have a look at the real center. Here we have the CO322 that was modeled with the kinematics. And in the real center here, there was this feature, red shifted, that could not be modeled by simple rotation. And we have a kinematical correspondence with the H1 clouds, which has also redshifted at the same velocities. 2 minutes, perfect. And so here, and so this is proof of fueling of the AGN, and again, multi-phase. Now, really quickly, we'll show you nice images about Fornax A, where you have, we proved studying the multi-wavelength emission in the radio, that we have a recursive activity given that the spectral index, the frequency break of the features of the lobes and the jets are different. Now, what fuels this recursive activity is clearly the gas that we could identify with the same observation in the neutral hydrogen. And the resolution back in the time was not enough because this was commissioning of Meerkat. So we combined information again with the CO120, but also with the ionized gas with MUSE. And here you see this filament that is not clearly rotating. And also we identified some very broad lines that we related to an outflow entrained by the AGN. But what I want to focus you in the last 30 seconds is on this filament here that has very narrow kinematics and is seen both in the H1, here in green, and here you see the kinematical plot with the shift with respect to the systemic velocity and the dispersion. So if this was the outflow that you saw before, this is the rotating gas, and this is the filament perpendicular to the jets. So, and you see it also again with Muse in the ionized gas. The ellipses are the predictions of the kinematical conditions of gas that is cooling because of chaotic cold accretion. So we have a consistency with the kinematics of a model that tells you that cold chaotic accretion may fuel the AGN and possibly the recursive activity that we identified in the continuum. Again, combining also the physical conditions so we can measure the cooling time of these different features, we see that the cooling time compared to the eddy turnover time is compatible with 1, which means that turbulence is acting for the cooling of this filament that is likely then falling towards the supermassive black hole. So, in my conclusions, I hope to have convinced you that in this NGC 3100, cold gas is fueling the AGN from the circumgalactic medium and fueling the circumnuclear disk, but also falling directly with clouds onto the AGN. While in Fornax A, the recursive activity that you see here in the jets and in the lobes is likely fueled by chaotic cold accretion of gas that is cooling in the innermost 6 kiloparsecs that you see here. Now, the best thing is that with SKA, we will be able to do this with only one instrument plus ALMA. So go from the very low frequencies to study the activity of the AGN and combining with SKA mid, so we can have the information at 1.4 gigahertz and also of the H1. Thank you.
Thank you very much. Questions? Here.
Oh, thank you very much. Really interesting talk. So I was wondering if you have a way to estimate the inflow rate or the fueling of the black hole and comparing it to the emission from the AGN, from the luminosity or the volumetric luminosity.
So of course we how do I go back? Red, I guess. So when in NGC 3100, for example, which is a easier case, because as you can see here, we can measure, now we have also the spectrally resolution of 1.4 kilometers, and we can resolve these two clouds and estimate the mass, also from the CO emission, and then we have an inflow rate that we can assume could be given by these two features, and then we can compare it to the luminosity of the AGN and the jet power, for example. Yes. Well, for this galaxy I didn't, but for Parks 1718 that you saw previously, it's in the ALMA papers, so it's possible to be done. Yes.
Okay, there was another question over there. Yeah. Just wait for the mic. Yep.
Hi, Filippo. Great talk. So what's the angular resolution and the amount of redshift that you can say comfortably conclude that this gas is infalling for any given observation?
Well, the trick is always to combine H1 and ALMA, because the resolution comes then from ALMA. And again, here you have, in this case, in the CO322, you have a subarc second resolution. Sorry, where do I go? This way. Okay. So here you have a subarc second resolution that allows you to really point within, for example, in this case, 20 parsecs, 30 parsecs.
Use the mic if you can.
So it depends. Yes, but I mean, it depends also. These galaxies are nearby, so it's easy to reach these resolutions. But you can, of course, do it with ALMA. With the Meerkat, you're limited to 7 arc seconds, but then you have you see the absorption, and so this, since you can collocate with the kinematics, it tells you, it improves, if you want, also the resolution of the H1 in this case.
Thank you.
Okay, I think we better leave it there, and let's thank Filippo and all of our speakers this morning.
Hello, everyone. We'll have another session starting here in another few minutes. So if you're welcome to join us if you want, but yeah.
Hello. Is it possible to test my slides? Can you hear me?
Hello, can you hear me? Yes.
Yes.
We just need a couple of minutes just to set up the room, and then we've got your presentation.
Ah,
Will you
okay.
side?
Um,
Please just give us a few minutes, and let's say 2 to 3 minutes, and then we'll get everything sorted out.
okay, thank you.
Give us 2 to 3 minutes so we can get everything ready.
I hope it will work because we didn't test it now. I was online for 45 minutes, but there was nobody there.
Okay, hold on 1 second. Please 1 second. Coming to you.
Okay, I ready?
Presentation.
Yes.
Hello.
Hello.
Can you hear us? Oh, okay.
Yes, I can hear you.
Will you be sharing your presentation?
I can do if I'm supposed to, I will do that. I cannot share while someone else is sharing, it says.
So you're gonna have to share your screen on your side so we're able to see it.
I got the message that I cannot share my screen while the
Oh.
other participant is sharing.
Okay. So I'm gonna check that.
I think you are sharing the screen, so I can't share. No.
Okay, we've
I,
stopped
I,
sharing.
I try again. Share. Oh, 1 second. Can you see it?
Okay. Hello, everyone. Welcome to the afternoon session. Sorry about the late start. We had to prep quickly after the previous lunchtime session. And we're going to be continuing to talk about feedback. We have a couple of online talks and the schedule has changed. Unfortunately, the last speaker won't be able to join us anymore due to illness. Speakers, I'll give you a 5-minute warning or a 3-minute. If it's online, I'll do it by the microphone so that you can hear me. The clock is down there and it includes your question time, okay? So be aware of that. But to start with, we have Steffi Walsh, who's going to be talking to us about feedback.
Yeah, thank you very much, Rowan. Yeah, so first of all, really thanks to the organizers for putting together such a wonderful program. I hope you can hear me okay. Yeah, I'm very sorry that I cannot be there. I'm involved in a large grant proposal and it's taking all my time, so I couldn't travel. All right, so I will try to provide you an overview of recent theoretical and computational works on the impact of stellar feedback on the cold ISM. And yeah, please excuse my lack of incompleteness, my lack of completeness, not incompleteness. Well, it's the 20 minutes which are the reason for it. So let me start by mentioning some open questions, which I found are the most important. So we are looking into the question of what is the dominant feedback mechanism, if there is such a thing as the dominant feedback mechanism. It is quite likely, and I will show you during my talk, that the answer is not simple and that it depends on things like, of course, the environment with which the stars or the things which cause the feedback interact with, but also about details like metallicity, binarity, cluster mass, etc. And further, we will look into how the relative impact of the different feedback processes changes with galactic environment, for example, and also with spatial scale a little bit, although I cut out the protostellar feedback since I don't really have time to go into this. So if you have questions later on, please contact me. And so also I assume that stellar feedback will change across cosmic time, mostly because of the galactic environment conditions, which are probably changing across cosmic time. So in this talk, due to the high dynamic range, studies of star formation and stellar feedback over long time scales are computationally very demanding. And in this talk, therefore, I will focus on scales of kiloparsec and below. So this means that I will not review galaxy formation work, which looks at the impact of feedback on larger scales, although they studies, in particular on dwarf galaxies, which are very sensitive to feedback mechanisms. Let's start with feedback from massive stars. So massive stars are extremely rare. We believe solar masses of gas that goes into new stars, and therefore massive stars are special. So they have short lifetimes of just a few million years, and they die as supernova type 2. And so here you can see a plot by Philippe André, basically showing how the IMF is related with the prestellar core mass function and the mass function of CO clumps. And massive stars, we talk about stars which have more than 8 solar masses. So you can see that basically they are not even on the plot. There are so few of them. However, they are very important because they emit a large amount of ionizing radiation during their lifetime. And ionizing radiation heats up the environment to about 10,000 Kelvin, disperses the surrounding gas, and we will look into how this comes about. And they also have fast stellar winds, which with mass loss rates of typically something like 10 to the minus 6 solar masses per year. These massive stars are like shedding their outer layers, and the velocities are extremely high, a few thousand kilometers per second. So these stellar winds provide momentum input, which obviously cannot be dissipated, but still there's a debate on how efficient stellar winds are compared to ionizing radiation. What you can see here is stellar evolution tracks, so the luminosity in radiation and in stellar wind as a function of time for stars with different masses when they start out on the main sequence. And also with different metallicities. So you can see here the Milky Way model in blue for 2 different tracks, for the Geneva tracks in darker blue, and the Milky Way tracks from the boost, the Bonn optimized stellar tracks in this lighter blue color. So there are also some differences in the stellar evolution models, as you can see here. And in particular, when you go to lower metallicities, these differences become more severe. So in this case, I only had the tracks from the boost models for the lower metallicities. That's why I'm showing them here. So here we have LMC, so 0.5 solar metallicity, 0.2 solar metallicity, and 1/50. And yeah, the lifetimes become shorter for lower metallicities. The wind impact decreases with lower metallicities because of reduced line driving. Now, going back to solar metallicity for now, if we look at the cumulative energy input of just 3 different stars here, 12, 23, and 60 solar masses, and we compare the total amount of energy emitted with the energy which you typically get from a type 2 supernova, so 10 to the 51 ergs, then we can see that the energy in the wind is way lower than the energy in the radiation. Only for the most massive stars, you get something from the wind comparable to the supernova. But just looking at that, we might think, well, why would we even care about wind at all if the radiation is so dominating, and then in particular the supernova are next? So now the thing is that we don't fully understand yet how the radiation couples to the ISM, meaning that it translates the radiation energy which is emitted by the stars is transformed into thermal or kinetic energy of the surrounding gas. And this efficiency is very low, so probably only 0.1% or so of the radiation goes into thermal or kinetic energy of the surrounding gas, meaning that you bring the radiation down here into a regime where we are comparable to supernovae or below. And so then there's an additional point which we should consider, namely, so if you look here at this nice plot from Agatz et al. From 2013, you see for a typical stellar population, time evolution of the bolometric luminosity output. Again, this is way dominating over everything else, but this coupling is the question, which I just mentioned. But then you also see that the radiation and the winds, of course, they they basically are there from the start when we start the evolution of the stellar population. However, the supernovae only come in after a few million years when the first massive stars die. And so then also the luminosity goes down because of the death of the massive stars. But still, so this early stellar feedback is the only thing which we have within the first few million years. And so latest observational results, and so Adam has mentioned this yesterday, that there's a hint of pre-supernova feedback being important for regulating the star formation efficiency in cold gas clouds. So now the question is about this transfer of input energy to energy of the surrounding gas. And I want to make an example here for stellar winds. So for example, for stellar winds, we have the momentum which is put in. So the mass lost at a given velocity. And this is what we would understand as the momentum-driven wind. But then at the same time, when the wind material is interacting with the surrounding gas, it heats up the surrounding gas and a hot bubble is formed. We can sometimes see it in X-rays. And this hot bubble is expanding, and there's an additional momentum input due to the hydrodynamical effect, so the pressure gradient across the interface of the wind bubble and the surrounding medium. And so in particular, if you just look at the energy put in by the wind, then you could also derive something like an energy-driven wind phase where you assume energy conservation. So this would be like the other extreme, so to say. And what kind of solution you actually get depends very much on how much energy is lost by cooling, mostly in turbulent mixing layers, which are extremely difficult to resolve. And I will show you now that the difference is enormous between these two cases. So if we look at the energy-driven wind first, then we can simply relate the total energy provided by the stellar wind and the total energy which is needed to unbind gas from the molecular cloud. And this is assuming a very simple setup, a spherical molecular cloud with some reasonable escape velocity of around 10 kilometers per second or so. You can put in anything you like. The escape velocity is here in the formula. But then the total energy that is provided by the wind is, of course, a sum of the wind energy input from individual stars, but then also factoring in how many massive stars you actually form per solar mass of gas that goes into stars, and how efficient the wind is. And so what we find when we do this relation, so this is assuming basically an adiabatic evolution, so no cooling. If we do this, we find that the winds are extremely efficient. So these energy-driven winds are able to unbind up to 100 times the mass of the formed stars. So this could reduce the star formation efficiency to 1% or something like that. However, if you look at the momentum-driven wind, where basically what you get is the wind momentum from the mass loss, again, you have to factor in the number of massive stars formed, and then you get the momentum input by an IMF averaged massive star population, and you relate it with the momentum which is required to unbind gas from this spherical gas cloud, then you can derive the efficiency of these momentum-driven winds, so basically assuming maximum cooling, and you find that actually the momentum-driven winds are basically not doing anything. The star formation efficiency could be as high as 90%. And the uncertainty here is this momentum boost factor, which is related to how the wind heats up the gas in the surroundings and causes an additional pressure acceleration due to the pressure gradient across the wind bubble edge in the momentum equation. So you can get any answer, so to say. So let's look in more detail at state-of-the-art simulations on the topic. And here I want to point out the nice papers by Lancaster et al., where he looked at clouds with 100,000 solar masses with different sizes, meaning that you increase the density and the surface density of the cloud as you shrink the mass, the 10 to the 5 solar masses to a smaller volume. compress it basically. And he also derived an analytical model to describe the cooling of turbulent mixing layers, which he used in these simulations. And so interestingly, what you find here is that the efficiency with which you cool depends on the environment very much. You can see this immediately here from these two images, so showing the temperature of the simulation of the simulated gas. So here for the more diffuse cloud, the wind is able to heat up the gas substantially. And here for the compressed cloud, the wind is basically not very effective. Everything is quite cold and is not really, the wind is not able to drive a proper bubble. And so this causes, although you have more star formation here, the star formation efficiency here is about 70%, and here only 28% or so. Nevertheless, the momentum, which is the radial momentum, which is caused by the stellar wind, is actually similar in both cases, meaning that the momentum input you get per stellar mass formed is much lower in the dense environment than in the low density environment. And so this we can kind of quantify as the so-called feedback yield. Ostraker and Kim introduced this in 2022, and it's been used in the to analyze observations of galaxies, which we have seen previously in this meeting. And so basically, it kind of quantifies a specific momentum that is delivered by the feedback. And so typical values for this are like 1,000 to 3,000 kilometer per second. Now here are factored in the solar mass, because in principle you get a momentum in solar masses kilometer per second, but then you divide it by the amount of mass that goes into stars, so to say, so another solar masses. So that's why you end up with kilometers per second, but it's not a velocity, it's really a specific momentum. And when we look at these values from Lancaster, we see that for these simulations, for the winds, we only get something like 100 kilometers per second, so much lower than what we need in order to regulate star formation to the observed levels. It's not surprising that winds are not very efficient. We see this in previous simulations. So for example, here from Dale et al. 2014, or also in his review from 2015, where he compares the impact of ionizing radiation and stellar winds, and finds that the winds are basically negligible, but these are actually momentum-driven winds in these SPH simulations, so it's also not a surprising result. But for these lower mass clouds, we actually don't have such a problem to unbind gas. For clouds which have escape velocities of 10 kilometers per second or less, it is easy to unbind the overall cloud mass by ionizing radiation. And the ionizing radiation is actually very efficient in dispersing clouds and shutting off star formation, which we showed here in an earlier work by me, but there are also many papers by Sam Geen and Jim Dale and other people. Let me move on. Oops. So, so because we have now already seen the importance of the environment for the effect of feedback, we can ask the question, what is a realistic environment? And so for that, we can look at the typical mass distribution in the temperature density plane of gas found in a multi-phase interstellar medium in a typical galactic disk environment. And so in red, you see the regions which are most populated, so basically where most of the gas mass is located. And so you can see that there's a lot of gas which is cold and neutral or molecular if you go to higher densities. So this is the CNM, the cold neutral medium, or the cold molecular medium down here. And there's also a lot of gas here around few thousand to 10,000 Kelvin at lower densities. So this is the warm neutral or warm ionized medium. Warm neutral would be here, below few thousand Kelvin or around few thousand Kelvin, and warm ionized above 8,000 Kelvin roughly. And we also know that stars form in clusters. So it means that maybe the first star, so stars obviously form here in the densest parts. So then at first they interact with the cold medium, yes, the cold and dense medium. But then since they live in a cluster, later on they would experience an environment that is already partially ionized or fully ionized, and where maybe some bubble has already been blown. And so the question is, how does the relative impact of ionizing radiation and stellar wind change as you go from a cold-dominated medium to a warm environment? And so we have looked at this in this paper with Sebastian Haidt, where we derived a semi-analytical model and also did numerical simulations to confirm the result. And so again, here I show you temperature versus density, and the color code shows the relation of the momentum which is delivered by the wind versus the momentum delivered by the radiation. So the blue color means that the medium is dominated by the impact of ionizing radiation, while the red color means that the medium is dominated by the impact of the stellar wind. And you can very clearly see that a medium which is already warm and partially or fully ionized will be dominated by the wind. The reason is that here the radiation does not couple very efficiently, so therefore a lot of photons just escape, and there's no real Spitzer bubble forming, because there is no cold environment which allows the formation of a hot bubble, with basically a pressure gradient across the interface. I think someone unmuted and now there's a feedback loop. Okay, thank you. Right, so again, this clearly shows that there's a difference depending on the environment. And since we have such a multi-phase ISM where all the environments come together, we need to consider both, or actually all of these feedback processes in the simulations. So we cannot just neglect the wind because it's maybe ineffective in a dense environment. Then finally, we also have supernovae. And the typical momentum which is delivered by supernova ejecta is just few times 10,000 solar masses kilometer per second. And again, the supernova heats up the surrounding medium to about 1 million Kelvin or more. And the formation of the hot bubble again causes a hydrodynamic effect, and therefore an increase of the net momentum which is delivered to the surrounding medium. And this means that the final momentum input by a supernova is actually boosted compared to the momentum input from the ejecta. And how much it is boosted, again, depends on the environment. Because if you have denser gas, the radiative cooling will set in earlier than if you have a low density environment, and you can have a very large bubble driven by the supernova. So typically what you find is that the boost of the momentum is about a factor of 10 to maybe 30 or so, meaning that instead of 10,000 solar masses kilometer per second, you will get something like 10 to the 5, few 10 to the 5. If we again put this on into our feedback yield, then we have to divide by the fact that we get one massive star per 100 solar masses roughly, so one supernova per 100 solar masses. And this gives us then a feedback yield of around 1,000 to 3,000 kilometer per second. This doesn't consider that some of the some of the hot gas is actually blowing out, and maybe, so this is like an upper limit, I would say, but it is already in the same ballpark as what we need in order to explain the observed star formation efficiencies in galaxies. But as we've seen previously in the plot by Oscar Agatz, the supernova act too late to efficiently regulate star formation in an early stage, because they need several million years before they actually explode. And so therefore, if we now do simulations of the multi-phase interstellar medium, we can switch on and off different feedback processes.
That's time, Steffi, just so you know, okay?
Sorry?
We're at time, Steffi, just so you know, okay?
I didn't get it, sorry.
It's 20 minutes.
Oh, it is already 20 minutes, okay.
It's no bother.
Right. Yeah, so I wanted to show, really? Because I started at, okay. Yeah, sorry, I'm too slow. So, okay, I wanted to show you that many other people are doing this work. So we can see basically that supernova explosions are not really efficient in regulating star formation down to the observed level, and that we really need radiation or stellar winds, so early feedback to pull down the star formation to the observed level. However, supernova feedback is relevant because it is actually able to drive outflows. So due to the fact that you pressure the disk that you cause very high thermal pressures in the disk midplane due to supernova explosions, you can actually lead to high volume filling fractions in the disk midplane. And if you manage to do that, you can actually quite efficiently drive fountain flows and outflows. And this is shown here by relating the mass loading, so the outflow rate over the star formation rate, with the hot gas volume filling fraction in the disk midplane. And so you see that disks which are relatively cold also don't have a significant mass loading, while disks which are substantially driven by supernovae can actually have quite large mass loading to the extent that it's actually unrealistic. So this is when we make the conditions so that you basically have a little starburst. Since I'm running out of time, I want to mention, however, the feedback mechanisms which I didn't talk about so far, and which we are looking now into in more detail. So cosmic rays are accelerated in strong shocks, for example, in supernova blast waves. And there's a lot of work about this, looking at the cosmic ray input spectrum and so on. And what we can do in our simulations is that we put in cosmic rays for every supernova explosion and then develop the cosmic rays as a fluid. In fact, the simulation you've just seen included cosmic rays. We can also look at the radiation pressure and at lower, so non-ionizing radiation, FUV radiation, which also comes from lower mass stars. When we do that, we can go also to higher surface densities in our studies. And we can see that with the inclusion of all these feedback mechanisms, we are actually able to explain the star formation rate surface densities observed in different types of environments. And I want to show you the impact of cosmic rays here, because this has been mentioned by Diane before, that there is cold gas which is observed in the outflows. Now, if you do a simulation without cosmic rays, the gas you get into an outflow is very hot because you need to have this very high pressure to launch gas and to keep it going outwards. But if you have cosmic rays, we are actually able to launch colder outflows because the cosmic rays also develop a pressure gradient in the vertical direction. And so they act like an elevator for the gas. So the cosmic ray pressure gradient is coupled with the momentum equation of the gas, kind of lifting it up once you have made it, once you have pushed it out a little bit. And so you see here the sound speed of the gas. And so we do have cold gas here. Here is plotted the energy and the mass in the outflow. And you see that it's substantially colder than without cosmic rays. So this is the most important thing here. And before I finish, I want to show you one nice thing which we are looking into right now, what other things cosmic rays can do. So we think that actually cosmic rays are not so important for the star formation in solar metallicity gas. So this is what we have seen so far, and we never assumed that cosmic rays are actually important for star formation locally, because they diffuse out very quickly, and so they also on the scales of star formation, you know, the pressure gradient is not very strong, so it averages out quickly. But what we found recently—
That's 25 now, Steffi.
Sorry, yes, I finished. What we found recently is that the cosmic ray heating might be important for low metallicity gas, where it can be more relevant than the photoelectric heating. Okay, and with this, I will finish, and I will leave up my conclusions. 1 second here. So, and yeah, thank you for listening. I hope it was okay, despite the fact that I wasn't around.
Thank you very much. Okay, I think we've got time for one question. Could the next speaker come up and set up at the same time, please?
Right.
Okay, one question, anyone? No? Yeah, over here.
Yes. Thank you so much for the talk. So I'm just wondering, what is the main driver of the phase transition from WIM to CNM?
Yes, you mean here? I don't have time to go back there. The main driver here, so that it's both ways. So on the one hand, you need to cool down the gas. So here you have compression by shocks. So for example, you sweep up shells in around supernova bubbles or around H2 regions also. And then you can basically cool down the gas. On the other hand, you also heat up the gas, right? When you go from the cold medium and ionize it and push it apart. So what you get here is like a mix of both processes. And in fact, the branch here at higher densities and intermediate temperatures, how much it is populated depends on whether you include ionizing radiation or not. Yeah. So this is what we find. And maybe just a heads up. So we have recently looked into this variable far ultraviolet radiation. And what we find there is that actually there's less gas in the thermally unstable regime if you take this into account. So there's a nicer phase transition in this case. But yeah, no time to talk about it.
Thank you very much, Steffi. Let's thank her again. Our next speaker is Tom Oosterloo.
Yeah, thank you. I will be talking about work we've done with ALMA on the radio galaxy 3C84. And the context in which we did this work is to work in the overall picture of the impact of radio AGN on the feedback of radio AGN in cool core clusters. The feedback of radio jets is in two phases. This is here, you see the first phase when the young jet is embedded in the interstellar medium of the galaxy, say more or less the gas disk of the galaxy. It works its way out and disturbing and pushing out the gas. There is a second phase, a later stage, where the jets have left the galaxy and they are in the hot gas that is surrounding the central cluster galaxy. This is, I'm not sure it's working. Oh, yeah, it is. This is 3C84. Here are the radio jets, and the image is the X-ray gas. And you can see that the radio jets are inflating bubbles in the hot gas, and of course affecting the conditions of the hot gas. And this is thought to prevent or reduce at least the cooling of the gas in the cluster. The question that we have, okay, this affects the cooling of the gas and the whole hydrodynamics of the gas in the galaxy. But some gas still has to cool, and for example, to keep the AGN active. And this is why we choose this object to study. What can we learn about the distribution kinematics of the cold gas, the cold molecular gas that is affected by this radio AGN. And we have two papers on this. I will only talk about the second one. The first one is H1 absorption. I will show one plot at the end of that. But what I will talk is about recalibrated ALMA observations of CO221. This is 3C84. It's a famous radio galaxy at the center of the Perseus cluster. And the environment of the galaxy is very rich in gas in all phases. I showed the X-ray emission. That's again, this blue is the X-ray. The contours here is the molecular gas, CO, observed by Salome, and there's about 10 to the 10 solar masses of cold molecular gas in the center of this cluster. So it's a very large amount. On very large scale, this is tens of kiloparsecs. There are filaments of H-alpha emitting gas, so ionized gas. Very large system. This bright part of the H-alpha corresponds more or less to the large molecular reservoir. So the idea of this galaxy that there is a mix of heating and cooling processes going on, basically driven by the radio jet. The radio jet enters the hot medium, inflates bubbles, heats it, but the idea is that around the edges of these bubbles, gas can still cool and is thought to fall back to the center of the galaxy where it may feed the AGN. What was known from observations, this is warm molecular gas. This is the inner part. This is 100 parsec, so this is inner few hundred parsec. This is the warm molecular gas, and what you see is a fast Keplerian disk surrounding the black hole, and that is surrounded by a less regular circumnuclear structure, disk-like structure. It's sort of rotating, but you can clearly see it's not a relaxed system. On larger scales, this is now 2 kiloparsecs, so this plot is in the center here. This is also molecular gas, CO2 to 1. You see that on the very large scale, there are filaments of cold molecular gas pointing towards this center of the cluster, the center of the galaxy. So the question is, are these now filaments of cold molecular gas that is feeding this molecular gas disk that you see in the warm molecular gas? So an attempt was made by Nagai in 2019, observing with ALMA, and this is more or less, this corresponds to the inner part of this circumnuclear disk. This is the velocity field of the CO, and you can see it doesn't show very much. It's quite irregular or noisy at least, and there is a good reason for that, because 3C84, also at these frequencies, say 200 plus gigahertz, is one of the brightest sources on the sky. It's variable in time, but it's roughly 10 Jansky. So it's very difficult to get a good bandpass calibration, say, or in effect, the signal to noise in your bandpass calibration, if you follow the normal procedure, the signal to noise is not sufficient to calibrate your spectral response of ALMA. And this is a movie of the channel maps when the continuum is removed, or at least we attempted to remove the continuum. But because the bandpass calibration is so bad, you see that there are still residuals in the image. And in radio astronomy, the PSF extends over the entire image. So it does not only affect the center, but the entire image. You see all these stripes. These is residuals from the PSF that you cannot remove in the standard way. So what we did is a sort of a trick. We did a spectral self-calibration. So normally you cannot do spectral self-calibration because if you leave the line emission in the data and you do the bandpass calibration, you calibrate away the line emission. But in this case, the continuum is so much stronger than the line emission that you get away with it. Certainly, if you iterate a few times, trying to remove the line emission, you apply it once, then you remove the line emission, you apply it again. And then you go from this is the original position velocity diagram of 3CH4, you get this. And you can very nicely now see the circumnuclear structure of the CO is very much improved in signal to noise. So the self-calibration, spectral self-calibration seems to work, except for the central beam. Any emission or absorption in the central position, where there is the continuum is strong, everything is calibrated away. So the fact that we don't see much emission or absorption here could be due to the calibration. So this is now the new movie. And you see now all these residuals are removed and we clearly see the filaments of the CO in this galaxy. So there's a big improvement. So what do we see? This is the old SMA map. This is what we now see here. So it's a large complex of filaments and clouds surrounding the circumnuclear disk that we now also image very well. Here you see the velocity field. Here is the circumnuclear disk with the Keplerian part and filaments with a relatively chaotic velocity field pointing towards the central circumnuclear disk. So just to zoom in, this is the circumnuclear disk now, and you see filaments connecting to it, also in velocity. If you do a position velocity map along slices here, you see that it connects, the filaments connect to the circumnuclear disk. This is a comparison with the warm molecular gas, and you see it looks almost the same. There's the circumnuclear disk, then in the warm molecular gas there is this sort of counter-rotating tail that we see here. And also this filament here is nicely visible in our CO data. So what our data now show is that these irregularities that you see in a warm molecular gas are due to filaments of cold molecular gas flowing onto the circumnuclear disk. So this closes then the feedback loop in this galaxy. So the jet stimulates heating and cooling, and in the end, at least some of this molecular gas falls back to the AGN. Next step is that this is the show. The observations have all HCN and HCO plus. And you can do the same trick, and then you can look at line ratios. And you see that the line ratios vary strongly with radius. We haven't done the proper analysis. That's what we are working on. But you can see that that the line ratios are a strong function of radius, so they will give us very good information on the physical conditions within this circumnuclear disk and its surrounding. So that brings me to my last slide. So we have reprocessed these ALMA data, and with very nice results showing molecular filaments flowing onto the circumnuclear disk and probably in the end feed the AGN. We also did H1 observations, and we also see this circumnuclear disk in H1. This is the velocity field is the CO velocity field, and the contours is radio continuum. This galaxy was known to have H1 absorption since decades. It's one of the famous systems. And it was also always thought that the H1 absorption is against the bright continuum. Turns out not to be the case. There's no absorption against this bright continuum source, but the absorption is against this circumnuclear disk. That must be star forming or something. Because if you look at the H1 profile, it shows the same kinematic signature as a molecular circumnuclear disk. So we also see this circumnuclear disk in H1. Thank you.
Thank you very much. So we've got time for questions. You have a microphone over there?
Thank you. Very nice talk. I was wondering if you can also connect the time scale of the jet and so the AGN activity to the recondensation of these filaments. So, because you say that the jets expand and then these clouds cool, but in how long do they cool compared to the activity?
Oh, the continuous activity is more or less continuous. It goes up and down. It's quite variable. It varies on the time scale of 10, 20 years, even varies a factor 2 in flux. So what our idea is that because every once in a while a filament is falling into it, the activity increases. So you get new bubbles. The jet may reorient a bit because the angular momentum is not the same. So sort of a continuous process of heating and cooling. Yeah.
Alberto?
Tom, beautiful data and very clever recalibration. So what do you think is happening with the velocity field in the filaments? Because you showed that it was very chaotic. So what is going on?
What we think, maybe sort of, there are these models of chaotic accretion that sort of, the gas comes from a large radius. So it may have some angular momentum, but not necessarily fully rotating. So it depends where it comes from. It falls in either, say, clockwise or counterclockwise. Because there is no net angular momentum at large radius. So they sort of radially fall in, but they may have some, by accident more or less, they have some angular momentum. And one filament, and if you look at the velocity field, at the same location, you have a counter-rotating and a co-rotating filament. So it's just depending where it came from. We don't see say a large-scale pattern in also the H-alpha velocity field on this H-alpha filaments on very large scale is sort of a chaotic structure.
Do we have any more questions? Got time for another.
Thank you. Just to follow up on that one, so the H-alpha filaments overlap with the CO?
That's a good question. We don't have the data to make actually that comparison. There are integral field optical observations of the filaments. And it covers very nicely this large area. But if you look at the data, there is a small central hole in the data queue that exactly corresponds to the primary beam of ALMA because it's too bright for them. So it burned out. So in principle, you could check it, and we expect to be a connection between the two, but observationally, we don't know.
Okay, thank you very much. Let's thank Tom again. And could our next speaker come up now, please? So next we have Henko Arlo, who's talking about the gas content of luminous compact blue galaxies.
Okay, hello everyone. Yeah, so I'm Henku. I'm a PhD student at the University of Cape Town, and my talk today will essentially be about my recently completed master's work under supervision of Professor DJ Pisano and Matthew Pasady. Okay, so luminous compact blue galaxies, what are they? This is a subset of starburst galaxies that are quite abundant in the early universe, and then their number density drops down quite starkly as we approach lower redshifts. This makes them a very rapidly evolving class of galaxy, and thus very good candidates for studying galactic evolution as a whole. What makes an LCBG an LCBG? Essentially, it needs to meet 3 cutoff criteria. It needs to be below a certain threshold in terms of its B band luminosity, its B minus V color, and its surface brightness. If it meets these 3 criteria, it's an LCBG. Our goal was to try and quantify the evolution of these objects in terms of their neutral hydrogen mass across redshift, as well as their specific star formation rates. So the data that we used came from the Cosmos H1 Large Extragalactic Survey, or CHILIS. This is a 1,000-hour spectral line survey of a single pointing within the larger Cosmos region. It covers a redshift range of 0 to 0.5. And Cosmos is a very well-studied patch of sky, rich of ancillary data for our studies. Along with the spectral line survey, there was also a continuum survey done, the CHILIS Continuum Polarization Survey of L-band continuum data with really good resolution and excellent noise coverage. So the first thing we set out to do is to look for direct detections within the cube. We found 3. 2 of these were originally detected first by Dr. Lucas Hunt within the first epoch of the data. And then the third one at a little bit larger redshift is possibly an interaction between an LCBG over here and a non-LCBG over here at a pretty close redshift. But okay, so 3 galaxies isn't enough to tell us much about the evolution of these things. So often what we have to resort to is stacking. So as opposed to standard spectral stacking, a method that we employed was something called cubelet stacking, which is where you take, we have a catalog of the LCBGs within our cube. We know their spectroscopic redshifts. So what we do is we crop little cubelets around each of these spots where we know a galaxy ought to be. We then co-add them. And then from this, we can extract a spectrum, which is then indicative of the average properties of the galaxies in the stack. What's also nice about this method is you can do a stack of the cube's point spread function, and then deconvolve your cubelet with that to clean it. So over here, we show the noise coverage within the cube, as well as the number of LCBGs throughout it. And we decided to first do one large stack of galaxies within this region, because there's a large number of LCBGs. You know, in stacking, it's a game of statistics. You want as much as possible. But then also the noise behaves slightly better in this region. So when we just stack everything here as a first go, we found this. So over here, what we see is a clear spectral detection. And this is taken over an aperture indicated by this little box over here. On the right is a moment zero map taken over the channels with emission. Okay, so once again, this is great. There's clearly H1 present, but it doesn't tell us much about the evolution of this parameter across redshift. So we decided to split this up into 3 separate frequency bins. But then we started to see we are losing detections. So when we look at the lowest redshift bin, we see no spectral detection over here, nothing spatially as well. In the central bin, we see a little bit of a detection in the spectrum, and a little bit of localized emission where we expected in the center, but now it's accompanied by these noise peaks elsewhere in the cubelet. In the final, in the highest redshift bin, we see again detection over here, some bright emission over here, but it's non-localized. So when we do not have a detection, what we had to resort to is just to measure 3 sigma upper limits on the masses. But you know, these spots around here beg to be investigated a little bit further. So here just some of the masses that we calculated. I'm going to so what for this talk I just chose 3 of the noise peaks that we looked at further. So essentially, we took a spectrum at any of each of these points at an aperture of roughly the same size, did a 2D polynomial baseline correction, and then measured the integrated signal to noise within a similar integration region as in the as for the original where we expect emission to be, and then we basically compare the signal to noise. At the moment, we see that some of the signal to noise ratios do compare with the central emission, which means that something is definitely happening here. This is something that we still need to investigate a little bit further. Maybe it has something to do with how we clean it. Maybe it is something where we have to take a look at spectral stacking techniques versus qubit stacking, but this is still an ongoing thing. Then, okay, so here I show just some of the upper limits and masses that we made with the stack detections, or direct detections, and then for reference, some other direct detections made in the literature. Moving on to the continuum stuff. So L-band continuum is also a tracer of star formation rates. So what we wanted to do was explore a study that was first done by Karim et al. In 2011, where they proposed that specific star formation rate can be described as a function of two independent functions in terms of coefficients, and then okay, so two independent functions in terms of redshift and stellar mass. So then these functions can be characterized by these coefficients and these exponents n and beta. So the idea was bin all of our galaxies in terms of several redshift bins, and then also in terms of different stellar mass bins, and then for each. So here we are. We bin them all. We did a continuum stack of them all, and now the idea is for a given stellar mass, we plot specific star formation rate as a function of redshift, and then we do the opposite. For a given redshift, we plot specific star formation rate as a function of stellar mass. And then we fit these functions, and then we can extract n and beta, which has been done in previous studies, and then compare, what is the evolution of LCBG specifically looking like in terms of these parameters. So that is what we did. The lines are those two functions we fit to it. What we see is that in terms of redshift, we see that the larger stellar masses tend to, the star formation rate tends to drop more steeper. This might show it a little bit better. So here is this extracted n and beta parameters. And then these are previous studies done in the past. For the record, these are all starburst galaxies from previous studies, so just so we're comparing the same thing to each other. What we see is interesting for LCBGs. We see a deviation from like the current trend at the moment. We see that for higher stellar masses, this n parameter seems to increase, but our beta parameter does seem to agree pretty well with what's previously been studied. Doing pretty well with time, actually. So here I've got some of my conclusions. So we see clear evolution in the specific star formation rate of LCBGs. The specific star formation rate agree with the literature at the moment. What now is the plan moving forward is to focus on the whole H1 problem. What I suspect is it is a problem of statistics. So this is for my master's work. It finished a few months ago. My PhD is now going to involve expanding this LCBG analysis to the Leduma survey, which is a survey done by Meerkat. It's going to be it's narrower, but it's much deeper. And since we know LCBGs are quite abundant in the earlier universe, we are hoping to have more statistics. The idea is to write this up into 2 separate papers. And yeah, like I said, I would also like to do a little bit of an analysis between kubelet stacking and spectral stacking to see what would be more appropriate. So if anyone is any stackers in the audience, come talk to me. I would love to chat. Thank you so much.
Thank you. Thanks, Henko. Lovely work. Do we have some questions? Okay.
So when you broke your continuum stacks down into the larger number of bins than you had for the H1, some of those images also show little, especially like the lower right one shows some flux outside the center. Do you think that's statistical, or do some of these galaxies have companions and things that?
This might just be something due to the confusion limit of the continuum data. Yeah, but so I will say the aperture that we extracted the fluxes from is smaller than this box that I'm indicating here. Yeah.
Any more questions? Fabulous. Get my exercise.
So nice work. I was wondering if you have any estimates on mass fractions of H1 divided by the stellar mass of these objects. Any even upper limits? Do you have any idea on based on the H1 data that you got?
No, unfortunately not. No.
Thank you. Any more questions? Okay, then let's thank our speaker again. Okay, our next talk is online, I believe.
Hi, can you hear me?
Hi, Ivana, can you hear us?
Yes, can you hear me?
Fantastic. So
Awesome.
our next talk will be given by Ivana Beslik, and I will make sure that the microphone is on for your warning this time, because that seemed to be the problem last time. So please take it away.
Okay, first, can you tell me, do you see slides? Do you see the
We can see you fine, yeah.
Let me just quickly put in the presenting mode. Yeah, so let's start time. And yes, here we are. Thank you very much for a nice introduction. Hello, everyone. I'm very sorry that I'm not in person there, but thanks to the organizers, I have the opportunity to present my work and the work of my team online. And yes, in the following, you'll see some of the results of a joint teamwork of astronomers and data scientists on analyzing Orion B local giant molecular cloud, that it's also visible from Cape Town during summer.
You know that I'm going to do it. I'll stand up so you know to turn.
So this is the team. There are few PhD students, several postdocs, and many permanent staff all across France, but also from Spain and other institutes around Europe. And the team officially started in 2018. Visit our webpage to see all the work that has been done so far, because 10 minutes is not enough to present all of this. And yeah, so without further ado, I will move on. So the team gathered up to analyze observations conducted by IRM 30-meter telescope that's located in Spain. We mapped 3 to 4 millimeter window, the area that's actually shown in the background of this slide. That's Orion B. We invested around 1,000 hours to map this huge, enormous field of view at very high spatial resolution. And as you can see, some technical details here, the data set is so huge and enormous that we actually needed to team up with data scientists in order to properly analyze this data set. And hopefully at some point, this will be a nice example and give a push to other future upcoming line surveys, because in the future, we expect more data sets like this. So this is Orion B. As I said, it's visible from the Northern Hemisphere, but also from Cape Town. And in the bottom right corner of this image, you see a nice and well-known Horsehead Nebula. And overall, in the optical image, we see that there are some dusty and dusty obscured regions, but we also see some star formation going on. But when we move to radio wavelengths, the image changes a little bit. So now, for instance, the Horsehead Nebula, that's also on the bottom right panel of this slide, appears to be quite bright. And in molecular emission, that's actually this image, we see some filamentary structure. And we see that since each color here represents different molecular emission, we see that each line will be sensitive to different physical conditions of the gas. And this is exactly what we want to further quantify. So we are interested in understanding the properties of a typical giant molecular cloud to bridge the gap toward the extragalactic community, to derive some typical conditions such as density, column density, temperature, to derive and to probe the conditions that are sensitive to specific molecular emission, and also to gather this up and to interpret this result in the context of star formation theories. So now I'm going to present some of the work that has been done so far in our team. Each of these deserves a proper full talk. So if I missed to explain some details, please forgive me. So the first paper from our team was from Jérôme Petit, and basically these are the first moment maps of some of the lines we detected. So there are many more, and they are still being processed and analyzed. And to first order, you see here that each line has different spatial coverage, different signal-to-noise ratios. Some show a very distributed emissions, such as 12CO, that's the upper left part of this figure. And some of those, such as M2H+, are very faint, and they are tracing dense cores. But moreover, there are also some molecular lines that are sensitive to UV radiation, such as 12CN, to PDR regions such as HCl+, and so on. So this was the first result from our work, and further principal component analysis and also clustering algorithms that have been also published derived further the tracer, what are the typical tracers for each of these regions. And moving on, so we know, especially in radio astronomy, we really suffer the noise in our data sets. And that's actually something that we have to deal either by stacking, as already mentioned, or by maybe smoothing the data set. But a member of our team, Lucas Eining, that's a PhD student, recently published a paper where he actually applied a denoising algorithm in order to gain the signal in the low signal to noise part without disrupting the higher signal to noise areas. And for that, he used the autoencoder neural network, and the schematic is shown here on the left, and on the right you see the comparison between maps by just summarizing everything along the velocity axis and derived from after denoising, and we see a huge improvement, and this is something that can be widely applicable to other studies as well. Next, if you want to interpret our observations in the context of models, interstellar models are very complex and very time-consuming. So we usually use some interpolated pre-computed grids to do a proper comparison. The work from our team also developed a faster Bayesian framework to compute these grids that is more time efficient and more accurate than some of methods used previously to compute these models, such as interpolation. And this comparison, including the credential intervals, are shown on the right of this slide. Moving on, so as I said, we also wanted to estimate some parameters of the molecular gas, such as column density. That's usually estimated from dust. And to do that, this work actually used random forest, so machine learning, a supervised learning of machine learning algorithm to to train the model and to predict which lines are good tracers of column density. And basically the main result from this paper is that we have to use simultaneously several lines to do that, and together, depending on the specific region of the gas, if it's PDR or if it's more translucent or dense. So these some of the key lines.
7 minutes.
Thank you. Some of key line species are listed here, and the figure shows basically the contribution to column density of some of these lines on the example of the Horsehead, and you can see definitely that each line has different contribution depending on the region. Well, we're here at the Horsehead. So one of our PhD students actually analyzed the emission coming from different sight lines, and basically developed a model assuming that along one sight line we are observing different layers of gas, and created some sort of a sandwich model. And if you imagine that that sandwich is like a cheese sandwich, The foreground and background layer is bread, and the inner part is cheese. And basically, she found out that optically thick lines are mostly coming from the outer layers, so from the bread, and optically thick emissions such as C18O is mainly coming from the inner part, whereas some lines as HCO plus and H13CO plus have a contribution from both of these layers. Next, we also were interested in understanding the stability of gas in Orion B, the kinematics and magnetic fields. And these are these three studies that summarize this work. And first by Jan Orkish, he created a filamentary network of Orion B, and he found out that most filaments of Orion B are gravitationally stable, and those that are unstable are located mainly in NGC 2024, this Flame Nebula, and NGC 2023. In terms of kinematics, we found that Orion B consists of at least 3 layers, velocity layers of gas, so moving at different velocities, which is very important when interpreting emission line ratios and so on. And on the other hand, when it comes to magnetic field, we have found that magnetic field is sufficient to support gas against gravitational collapse in NGC 2034, which can, on the other side, explain lower star formation efficiency of this cloud. So magnetic field, for that is also important to have electrons, and we developed analytical models to trace ionization fraction in Orion B, and we applied for the first time this to real observations. Specifically, we used CN to N2H plus line ratio to probe to compute the ionization fraction, and we found that ionization fraction is 10 to the minus 6.5 in dense gas. And we also found that this is very sensitive to UV radiation, so further analysis is required to interpret our observations. And just the final minute to use to quickly explain that we also aim to bridge the gap toward extragalactic community, because what is our full map that's shown on the bottom left part, it's sometimes 1 pixel in extragalactic work. So within 1 pixel, we have the mixture of many different physical conditions of the gas, different temperatures, different velocities, and we have somehow to understand further this effect. And this is what Antoine has been doing. And he recently published a paper, and he basically investigated how this, how these parameters change with the beam filling factor, and found that the lines that are most sensitive to density, such as N2H plus, show the greatest variation that's shown here. And the final work is basically if HCN traces dense gas that's typically used in extragalactic community. In the case of Orion B, we found that this is coming also from the translucent gas. So further interpretation and further work on this connecting HCN from the Milky Way studies to extragalactic work remains to be answered. And this is the final slide, and I hope that I've shown the possibility that we can do and all the tools that we can apply to analyze such great data set that we expect to becoming more and more, because in the future, every observation will be technically a wide line survey. And with that, I would like to finish with my talk, to thank you for your attention. And yes, I'm ready for questions. Thank you.
Thank you very much. Okay, we have time for a question.
Thank you. Okay, thank you so much for the interesting talk. My question is about, you have just mentioned that you considered the methanol, but during your presentation is not presented. However, I want to ask about the at which frequency you are observing the methanol molecule. Thank you so much.
Thank you very much. So I don't know the specific frequency, but that's from between 76 and 116 gigahertz. So that's a few millimeter range. So one of the methanol lines within this range has been observed.
We have time for one more question, and could the next speaker come up?
Yeah, thank you for this talk. I would like to ask about the effect of building of the beam filling factor you showed, but very fast, so very quickly I couldn't see it. Yeah.
Yes, sorry,
Tell
we
about
didn't
that.
have time. So here are basically different lines. So from 12CO to N2H plus, and if you can, I hope that it's visible on the projector, the figures. So we see that they have they show quite of scatter. So this 12CO has like the largest beam filling factor, but the variation in line with NT peak that's basically caused by sub-beam averaging. It's small. It means that 12CO is not affected when we do in extragalactic work, but interpretation of N2H plus, this can be tricky because it's a small beam filling factor, but which causes the largest variation in measured line width and T peak.
Okay, thank you very much, Ivana.
Thank you very much.
Can we have the next speaker, please? Next, we have Thato Manamela.
Hi, my name is Tato Manamela, and I'm a PhD student at the University of Pretoria. How do I move? Okay, so I'll be presenting about how gravitational lensing can be used as a tool to study high redshift OH megamasers. So basically, an OH maser is just a cosmic laser whereby the OH molecule is stimulated by emission. On a spectrum, it is found on the 18 centimeter line, and it is characterized by the 1667 and the 165 main lines. And also it has satellite lines as shown on that spectrum, for example. And again, the prefix mega is just indicating that these sources are 1 million times greater than the ones that are observed in the Milky Way. So these sources are associated with major systems such as APR 220, and they have a far infrared luminosity greater than times 10 to the power 11 or times 10 to the power 12. So basically they are ULEGs or legs, and they have gas rich, high molecular gas, and they're dust rich or dust obscured. And again, they have extreme star formation. So as I've mentioned, the sources are associated with merging galaxies, meaning that they can be used as indicators for binary supermassive black holes. And again, they can be used to measure the galaxy measure rate of the universe. And again, you can also measure the magnetic fields via Zeeman splitting. So the problem about these sources is that they are rare and they're hard to find. So far, less than 120 of them are known, and majority of them were restricted to a redshift of 0.25. That's up until Meerkat detected the OHM megamaser in Galakata and the recent OH megamaser at a redshift of 0.7. So for my PhD, we plan to increase that redshift limit above that 0.7 by observing ULEGs using Meerkat and the UHF band. So as I've mentioned, we're using gravitational lensing to zoom deep into the cosmos. So our recipe is just gravitational lensing and assuming that the OH and far infrared correlation applies for sources at high ratios or ULEGs at high ratios. So this is our sample. Our sample consists of SDP sources such as SDP9 and SDP11 in H-Atlas 1324. So the sources are confirmed to be lens, and they have an average redshift or spectral redshift of 1.6, which corresponds to a frequency of 617 megahertz. So using the OH versus far infrared correlation, we predicted the OH luminosity of the sources. And on the blue curve is just representing the minimum detectable OH luminosity as a function of redshift for Meerkat for a 6-hour observational on-source observation using the UHF in the UHF band using the 32K correlator and the and the 16.6 kilometers per second frequency resolution. And then what we see that is that two of the SDP sources are below the noise. And then, however, we expect them to be boosted by magnification. So we managed to observe our sources for a 6-hour observation using Meerkat, UHF, 32 correlator, the same frequency resolution. And firstly, we did some radio continuum analysis. The image that I'm showing there is that of H-Atlas 1324. And our source is basically at the phase center, so we didn't have to do any primary beam correction. And the noise that we got for this full band continuum map is 5 microjanskis per beam. So zooming into the phase center, these are our radio continuum detections. And then as you can see, two of them, the radio continuum detections are in red, overlaid on the optical images. As you can see, the other two sources, H-Atlas 1324 and SDP11, they have more than one component. And then those two components are related to the nearby faint sources. So they are not basically radio jets. So our next step was to try to figure out what could be the dominating radio source of these galaxies. So we want to know whether they are AGN or star forming. So to do that, we firstly calculated what is known as the brightness temperature. And then from the brightness temperature, we found out these sources might be hosting AGN. Another thing that we did is that we compared the far infrared star formation rate and as well as the radio star formation rate. Looking at the radio star formation rate over there, you can see that it is much greater compared to the far infrared star formation rate, meaning that there are chances of a AGN in the sources. But however, according to the QFR, which is just the ratio between the far infrared luminosity over the radio luminosity uncorrected for lens magnification, and it shows that one of them indicates an AGN. And according to Condon 2002, if the ratio is below the 1.8 line, it means that this object has an AGN, and above that line, it's star forming. So, however, this phenomena, this AGN and star formation or extreme star formation AGN is common in merging galaxies, which is a transition from extreme star formation and the emergence of an AGN. But we believe that VLBI observations are required to find out whether the sources host AGN or they're just star forming galaxies, or it's just extreme star forming galaxies. And then for spectral analysis, these are our spectrums that we got. And looking at the H-Atlas 1324 and SDP11, we can see that there is no emission or there's no detection. However, the SDP9 is promising. We can see an absorption emission feature just at the positions where we expect the 166 line and the 167. So we believe that this source needs more integration time so that we can see what's happening. So since we didn't get any detection, we calculated the lower limits of the OH luminosity, and we compared it with our predicted luminosity, OH luminosities. And if that lower limit is greater than the predicted, it means that more integration time is required. As for as for HR class 1324, there's basically nothing there. Even though we didn't get any detection for one of our sources, we managed to get an OH detection at a redshift greater than 1. So this detection is just showcasing the power of gravitational lensing, and again, the sensitivity of the Meerkat telescope. So we got anyway, it has an SNR greater than 150, and it was only observed for 4.2 hours. And for conclusions from our 3 samples, there's a high possibility of a dust-obscured AGN, therefore VLBI observations are needed. We didn't get any spectral detection, but however, SDP9 is promising. And lastly, we managed to get a high redshift OH megasers with Meerkat with the aid of gravitational lensing. Thank you.
Okay, let's thank Dato. So do we have any questions?
Just to thank you for results. It's very nice. What is the line width? You're missing the velocity scale on the last plot. What is the line width? The velocity. Yeah.
Oh, so I can't really say much about this source since we are still going to publish it. So we're still busy with the lens modeling.
It's a very complex profile. So
yeah,
it's
it
very
is
interesting.
complex.
Okay,
Thanks.
thank you.
Thank you.
Thank you so much. Yeah, actually, I'm interested in OH maser part in the galaxy. So we know that the OH maser in our galaxies, especially in star formation, is coming from the disk, okay?
Yeah.
Or the circumstellar disk around the protostellar object. So what about the extra OH maser?
So
in the outer galaxies, where does it arises from?
It comes directly from the central core of this host. So it's coming from the center. I'm not sure if I answered your question.
Okay. Do we have any more questions? No?
So a very basic question. Maybe you say it and I miss it. What is the percentage of the ultraluminous sources that host an OH megamaser?
So the percentage, I'm not sure about the percentage, but there's no particular difference between legs that host these galaxies and the ones that, there's no clear evidence what is the difference between the two sources that host this emission and the ones that don't host this emission. Hence, that's why they are very hard to find. So I'm not sure about the percentage. I'm not really sure. But many of us have studied ULEX and LEGs, and some have failed. They didn't find anything. Yeah. So, okay.
Okay, last question.
Hi, thank you, Tato. It was a great talk. I would just like to know, can you elaborate a little bit on how the VLBI detections will help you detect whether it's AGN or not?
Okay, so for VLBI, we know that it can zoom in, it can resolve the core of the object. And again, it's much sensitive to the to sources with a brightness temperature exceeding times 10 to the power 6. So we can measure that brightness temperature. If it exceeds that amount, then there is an AGN.
Okay, let's thank Dato and all the speakers for some lovely talks. Okay.
Because they don't hear you. I think there's one online. Good job. So as people are filtering back in, is Bob Shake here? Second speaker? No. Okay. All right. Well, we'll get started when we get started, I guess. Oh, wait. Sorry.
Setting up meet?
I guess that's... You got it? 2 minutes. Okay. So clock, this will be the same slide. I mean, you did this on Monday, right? So,
Yeah, we're here, yeah.
Exactly. And you know that's the full time.
Right. Yep.
So when do you want a warning?
I think as long as I have that,
okay.
Should be okay.
Okay. I would offer to give a 2-minute, 50-second warning.
What
Sorry.
minutes are?
2-minute, 53-second warning.
Okay, good. Be precise. Are we starting or?
Please go ahead. So welcome back everybody to the last session.
Oh, can I start now? Okay. Oh, thank you very much. First of all, I'd like to thank the organizers for inviting me to give this review talk. Obviously, this is a very broad topic, so I end up creating a presentation slides with ADS links to the references. So if you're interested, please download it so you can go to the papers with easy click. Okay, so as we have seen, different instruments that appear in this session can observe different phases of gas phase species or ice phase species. So grain surface reactions are very important because it can act as a catalyst to form more and more complex molecules. So JWST can observe ice phase, and NGVLSK ALMA can observe gas phase, and JWST can also observe hot gas. And first of all, why do you want to study astrochemistry? One reason is that we can probe different phases of star formation. For example, if the major forms of the carbon goes from ionized to neutral to CO, you may see abundant carbon chains with abundant atomic carbon. And when the CO freezes onto dust grains, you may see abundant N2H+, because CO can destroy N2H+. And after the protostars are born, it can evaporate ice. So complex organic molecules like this can go into the gas phase. Sorry, the pointer is not working. But anyway, just to let you know, the complex organic molecules, or COMS, are carbon-containing species with 6 or more atoms. So, and astrochemistry can also probe different environments. I'm pretty sure most of you have seen this layered picture of PDRs, but in actual molecular clouds, it may be as complex as this in this simulation. So ionized carbon or atomic carbon may still be abundant in the densest parsed. And another source of ionization rate is cosmic rays. So the x-axis is Coulomb density and y-axis is the cosmic ray ionization rate. And the higher energy cosmic rays can penetrate deeper into the molecular clouds, while lower energy cosmic rays can increase the ionization rate at the surface of the molecular cloud. So what they can do is that in starburst environments, atomic carbon can be more dominant form of molecular gas instead of carbon monoxide. And another factor that can change chemistry are shocks. So it can increase the temperature to thousands of kelvins. And that means that some of the gas have energy to sputter out ice. So methanol is one of the abundant molecules on ice, and it can be seen in shocks. And elements like silicon or sulfur can also be sputtered out. And it can also induce a high temperature gas phase reaction with the reaction barriers. So in different galactic scales, all of these are happening. So if you observe something in the galactic scale, you might expect effects from, say, galactic shocks, or you may get the effects of central starburst, meaning that you might have more PDRs or cosmic ray dominant regions. And if you go to molecular cloud scale, as you have seen in the Orion B molecular cloud, you can resolve different density structures. And I don't know what Microsoft is doing, but if you go to the filamentary structure on the top right, you may start to see denser clouds you can see in N2H+. And in sub-parsec scale, on the bottom right, you can see effects from protostars. So this is the outline of my talk. And let's see if I'm too ambitious going from galactic scale to extragalactic scale. You can let me know later. Okay, so I'll go from prestellar to protostar and talk about cloud scale chemistry and galactic center, and move on to external galaxy. So for prestellar cores, previous findings were that you see abundant carbon chains that are unsaturated. And that's true, but recent very deep studies like Hode or Gotham start to see more and more complex molecules, including some of the benzene rings. So that may be related to the original PAHs. So that's one mystery that we have to solve in this field. And JWST can also probe ice phase. So this ice age survey had observed ice in the absorption. And these are the clouds with the relatively low CO depletion onto the gas grains. So it's not as evolved, but you see relatively abundant ices like carbon dioxide, ammonia, and methane. So ice is already evolved at the early stage. If the protostar is born, you start to see sublimation of ice species into the gas phase. And some of the survey observed the complex organic molecules and detected COMs only in 60% of the sources. So you might wonder, is it because of the difference in ice composition, or are they sublimating differently? So JWST ice observations can shed a light on this. So for example, Joy's survey started to see similar ice and gas abundances, but those are only for COM-rich sources. And I heard that this Corino survey started to show some different story. Maybe desorption is more important rather than the ice composition. Okay, so if you go to cloud scale, similar to the one that presented by Ivana Veslik, you can compare that with the extragalactic sources. So this is the work done by Yoshimasa Watanabe sitting over there. And so the field of view is 50 times 40 parsec. And we observed many molecular lines. And the results are really similar to what the Ivana showed. So HCN is not tracing the densest part that is shown in red, but N2H plus is a better tracer of dense gas. And that's actually already being shown in the simulation like this. So hydrochemical simulation showed that N2H plus is much more compact. So this is the emission intensity, and HCN is more extended. But my observation in M83 center shows that maybe that's only for cold dense gas. So in the hot region, even though the column density is high, it is not tracing, N2H plus is not that bright. What will happen if you go to the center of the galaxy? So one thing is that you see higher cosmic ray ionization rates. So as I said, diffuse clouds tend to have higher cosmic ray ionization rate because of the contribution from lower energy cosmic rays. But overall, the galactic center tend to have higher cosmic ray ionization rate. So there's a recent paper that says that calculated the ionization rate from the gamma ray fluorescence. They say that there's no gamma ray excess to explain this high cosmic ray ionization rate derived from the chemistry. So I think it's important that we work with the high energy people to resolve this discrepancy. And another thing that's happening in the galactic center is that you see many comets, but some of them are coming from not hot cores or protostars, but others are coming from shocked clouds. So because of the sublimation from the shocks, you see lots of complex organic molecules. But you do see many complex organic molecules in protostars like Sagittarius V2 as well. So if you detect comets, you have to ask yourself, is it from protostars or shocks? So what would happen if you increase the star formation rate much higher? So we tried to answer this question, and we observed the starburst galaxy NZC253. It has the about 20 times higher star formation rate compared with our galactic center. And it covered the Alma bands 3 through 7. And we detected about 1,500 transitions, including cold cloud traces like carbon chain C4H or comps like ethanol. So you can see rich spectra. And as far as the comps go, the abundance over methanol is as same as hot cores and higher than that of the galactic center shock clouds. So that may indicate that these comets are coming from protostars because of the high star formation rate. And another thing is that we even have a higher star formation rate than the galactic center. So even though we observe the dense clouds, the ionization rates are at least 1 order of magnitude higher than the galactic center. So it is derived by ionic species like H3O plus or HOC plus that are usually unstable. So we model that with the chemical models and derive the ionization rate. Again, there was a paper that calculated the ionization rate from the gamma ray observations. So some of the values are close, some are maybe chemistry derived values are higher. So again, we have to think about why these are different. Okay, we obtained so many images, like 150 images from this alchemy survey, and it's not that easy to interpret that. So what we did is to do some statistical study. So principal component analysis is a very typical statistical study that has already been done for like Orion B studies as well. So if you don't know PCA, the basic idea is you extract something called principal components, and you can consider that as a real building blocks for each transition. So, and fortunately, so these were associated with some physical conditions like oval molecular gas or young or old starburst. And each transition have different components of different principal components. So by doing this PCA, we were able to categorize different transition, like different tracers, for example, shock clouds or young versus more developed starburst, or photodissociation regions, or something like that. And we had a very good undergraduate student, and he did not PCA, but something called non-negative matrix factorization, NMF, and it seems to be working even better than that. So stay tuned for that. So the picture we get is that, so this is the center of the galaxy, and we're seeing it edge on. And it might be that the shocked clouds compresses the gas and induce the star formation and moves like this. So that's probably what we're seeing in this center of the galaxy. Okay. So what would happen if we increase the star formation rate even higher? So I said that we identify some of the traces of young starbursts. So these are like COMS or high excitation transition of HC3N or vibrationally excited lines. And these are more prominent in LERCs or ULERCs. So these are extreme systems that you saw on Lorenzo's talk. And so it's extremely compact and extremely excited. And they see strong vibrational excited lines. That means that you might see a vibrational mode in JWST. So there are not too many observations by JWST, but there's this work by Buiden et al. And so these are not that compact in terms of the galactic nuclei, but still they see very excited CO. And that's in the starburst regions around the AGN. For some reason, the excitation is not that high, but also in that very excited starburst regions, they see molecules like HCN or acetylene, C2H2, and those are species that are abundant near protostars. So those are abundant in dense and hot regions. And they also saw like water ice, CO2 ice. So yeah. So I'm pretty sure JWST will show more and more results from goals JWST, right? Roberto is nodding, so. Okay, just to talk about the future perspectives. So in a couple of years, we'll have ALMA WSU, and we can simply get more transition in one shot. And one thing about NGBL and SK are that they cover lower frequency. So larger molecules have larger dipole moments. That means that the transitions are in the lower frequency side. So, from protostars to starburst galaxy, we can really dig into the lower frequency part of the spectroscopy. And the line confusion is much less in lower frequency. So I think we can do more detailed study with that. And I also talked about the NTH plus as a dense gas tracer. And with ALMA, we could do like HCN surveys, but for N2H plus, I think the pilot study is the best we can do. So if we really want to do the survey, yeah, we need the NGBLA. And but for cosmic granulation rates, I guess for the species that I have shown, HOC plus, we could use it, but Also, OH could be also used to derive the ionization rate. So I think we need the pilot study already with VLA for that. And as an extragalactic astrochemist, I think we need more models. So the current models have either good physics with very simple chemistry, or many species with less physics. So I think the poster by Shatter is a good compromise. And yeah, so this is a summary. So I think this is a very simplified picture, okay? So, but even for a galactic or extragalactic sources, I think we can say, like, for starless quartz, we can trace we can trace with the carbon chains or NVH plus, and for young embedded star formation, we can trace with comms or highly excited lines. And for PDR tracers, well, we know that radicals like CN and CCH can trace that, but for starburst environments, highly excited lines like CN 322 or something like that is actually tracing the starburst region. And we can also trace cosmic ray ionization rate with these species. So well, hopefully we can connect that with the terms that many of you are familiar with, like supernova feedback or supernova feedback. But we need more quantitative models to actually connect that. So thank you very much for your attention.
Before we go to questions, we have plenty of time for it. Is the second speaker, is the next speaker here? You're still missing the talk, right? Bob, Shake? Okay, so in that case, we'll plan to go to the third talk right after this, but also there's probably a few extra minutes for questions. So questions? Yeah, Ruth.
Yeah, thanks. Very nice. So to the left of this diagram, what might be a good tracer for emission in the cold neutral medium? Of course, there's C0, but in the old days, OH thermal and formaldehyde thermal, things like that. Cold neutral medium is hard to see an emission because it's so easily blended with broader lines from the warm neutral medium because it's mixed. So what do you imagine might be good to trace dark gas?
Right, so people have used OH or CH for that, but yeah, I'm not sure if that's really tracing like the whole cold neutral medium. So my answer would be like OH or CH with question mark.
Nancy, can you comment on the, how easy or how difficult it is to produce PAHs in the conditions of the molecular clouds? Because my understanding is that from the model standpoint, it was very difficult to produce.
I think if you actually run like bottom-up models from simple molecules, the models are still underproducing pH like molecules like benzene rings and stuff. So we really don't have a good understanding of like formation rates and stuff.
Thanks for a very nice talk. I was curious on the ice front. Is there some good knowledge about how quickly the ices can form versus like how quickly they go away when you're not in a very dense core or a very dense region of a molecular cloud? Just like whether or not we expect to see that in just the general vicinity of molecular clouds.
Sorry, like I understand like how quickly it forms, but how quickly it goes away is what it,
yeah. So if your coated dust grains like are no longer in the densest part of a molecular cloud, is there a time scale on which people think ices evaporate?
Yes. So you mean like UV desorption? Yeah. So you can well, you can calculate it, but it depends on the radiation strength. So it's always the balance of like how quickly it goes onto the grain and how quickly it dissolves. So it's already a balance. So you can model it.
Yeah, if I could just add to this. So thanks for, I caught the last part of your talk. So, sorry for not being there the full time. But we know very well from ground-based and Spitzer data of ICES that there is a relation with AV and that visual extinction, and that changes per molecule. So water ice starts at 1.5 magnitudes, CO2 a little bit higher, methanol is shifted yet further. So that is, at least for our galaxy, that's known, and there's also some Spitzer data and Akari data on, say, the Magellanic Clouds ICES. Even ISO had some extragalactic ICES already. So my question was actually more on another topic. I always hear this comment about that the line confusion will be less in SKA region, and I must confess I'm not fully convinced about that. At least some of the simulations and observations that we've done, you know, down to 3 millimeters or even longer wavelengths, the spectra can be just as complicated. So I'm just wondering, you know, has there really been a good study of that?
Well, of course, you may know better, probably know better than that, right? Yeah, but at least for like extragalactic source like alchemy, the line confusion seems much less in band 3. Like, so band 7, we start to see so much blending.
Is that simply a sensitivity issue? I mean, that's...
It's not really...
Because as you showed also, the lines become much weaker when you go to... So it depends on your science question also. If you need to go deep to see a certain molecule, then the others will start to pop up as well. So I'm just questioning this because I hear it so often at at meetings that it would be really nice if somebody could do a more detailed simulation.
Yeah, I never questioned that because for NDC 253, it looks much better in lower frequency, but you're right, we should model that. Thank you.
If there are no other questions, let's thank Donna Say again. I think we're going to the third speaker, right? So, is that okay?
So good afternoon, everyone. Thanks for the organizers for this opportunity. I just landed in Cape Town, so I'm a bit sleep deprived. But so today I wanted to talk about the feedback from low power radio jets on the gas reservoir of quasars as part of the QSO feed project that we are developing at the IAC in the beautiful island of Tenerife. So just to talk a little bit, introduce a little bit AGN feedback. So nowadays we understand AGN as a much more cyclic episode of in a life of a galaxy, and it can be really short and happen several times depending on the gas supply in the galaxy. When the galaxy is active, we know that they launch outflows. So the outflows are ubiquitous, at least in luminous AGN. And we know from observations and from theory that the outflows are actually multi-phase. They can be observed at the accretion disk scales and also to the circumgalactic median, but also they are multi-phase, observing several tracers. And today, I would like to focus on the radio mode feedback in galactic scale. So usually we associate radio mode to these very large lobes impacting the circumgalactic median. But for these quasars, it seems contradictory. I want to talk about radio mode on galactic scale. So we know from the hydrodynamical simulations that relativistic radio jets percolating to the ISM can create a cocoon of shock material that can drive multi-phase outflows. And the feedback from these jets depends on several parameters, such as the kinetic power and also the distribution of this clumpy medium. And one interesting result from the simulations is that one should expect that the higher the energetic of the jet, higher the impact of feedback. But actually, we are starting to see that it's the opposite trend. So here I show some the initial conditions for the ISM from a low jet power in the middle and a high jet power. And in the middle, we see that we have a higher impact on the galaxy because the jet is trapped into the galaxy potential for longer times and is able to produce more damage over a larger volume. And on the other hand, the high jet power is able to escape more easily the galaxy potential. So this new population of low powered galaxies or radio quiet galaxies are the most representative among AGN. So this will be crucial for the next NGVLA and SKA missions that we will unveil a lot of these galactic scale low power jets up to higher redshifts. And from the observational point of view, we know from some empirical relations that molecular winds and ionized winds, the energetics, the mass rate that they carry correlates with the bolometric luminosity. And this is agreement with the idea that the AGN wind can launch a fast wind. But when we look at this kind of correlations, we might think that the quasar mode is the only mode happening in this kind of empirical relations. But is it? We'll see later. So let me introduce briefly the QSO feed project. So we wanted to assess the impact of quasar and driven outflows on the galaxy properties. And the sample is quasar type 2, so obscure quasars. They are very bright and a redshift around 0.1. So these allow us to perform resolve studies. And these galaxies, they are radio quiets, but they all show a radio axis. So it means that they are quiet, but not silent. And these jets and winds from these quasars could be potential drivers of ionized and molecular outflows. So we have a sample of 48 galaxies in the QSO feed, and we are gathering a lot of observational data in order to access the multi-phase impact of AGN feedback. So let me start with the cold molecular gas with the ALMA observations of CO2-1 that we perform in cycle 6 with a resolution of 0.2 arc-second, that is roughly corresponds to 300 parsecs in this galaxy. And we see that these observations reveal a wide range of morphologies from these double peak structures, also some spirals. But when we were trying to search for these wings with high velocity gas based on the bolometric luminosity of this agent, we're expecting to detect very massive outflows, but this didn't happen. These outflows show very mild properties, velocities of 200 kilometers per second, and mass outflow rates that are well below these empirical scaling relations. So one thing that we propose that the AGN luminosity is not the only parameter to explain these outflows. And one thing that could be really important is the coupling between the disks hosting these galaxies and the winds and jets. And when we were looking at these observations, there was one galaxy specific, that is the teacup. So teacup, the name stands for this large scale bubbles that we see that resemble a handle of a teacup. And the nuclear hosts a compact radio jet that is almost coplanar with the galaxy disk. And we analyze CO2-1 and CO2-2 observations, I show here in the bottom panels, and they both show this double peak morphology. And if we look at the position of this compact radio jet in the center, it might appear that this jet is kind of pushing away the gas. So since we had the two transitions, we could perform the resolve line ratios. And we see here that the line ratio is enhanced in the direction perpendicular to the radio depth, as well as the velocity dispersion. So this might represent that the gas has a different temperature along this direction and is actually like outflowing. It is part of a lateral expansion. The same trend was already seen in other galaxies, as example as IC 5063, but this was detected along the jet, not perpendicular. And in the optical, however, we see this same effect of larger velocity dispersions in the O3, as seen by Megara and Muse observations, but in such a much larger scales. So this is the first time we find clear evidence of enhancement of velocity dispersion and gas excitation perpendicular to the radio jet. And all the observations had some characteristics that might be explained by the simulation. So we contact the simulators and we perform a simulation of a jet power of 10 to the 45 per second with a very small inclination related to the galaxy disk. And the observations, as I show here in the right panels, the green ones are the hot tenuous gas, and the orange one represents the dense molecular gas. And on the bottom panel on the right, we can see that the simulated velocity dispersion matches pretty well what we observe for the teacup. So what we learned from the simulations is that as the jet propagates through the ISM is going to get splitted and deflected several times, and carrying momentum in all the directions, including this direction perpendicular to the jet. But one thing I would like to highlight that the maximum velocities of this lateral outflow that we detected are less than 400 kilometers per second. That is less than the escape velocity of this galaxy. So this gas eventually will rain back to the galaxy in the form of a galactic fountain, and is acting as to redistribute the gas and metals in delaying new star formation in the galaxy. So we wanted to apply the same for all the galaxies that we had these two, the CO322 and CO221 transitions for the KSO feed sample. And here I show in the bottom, in the top panels, the line ratios, and in the bottom, the velocity dispersion. So as you can see, we can also see the contours in black on the top panels. The radio emission is compact, is not resolved, so we cannot draw conclusions as in the case of teacup. And also these galaxies seem to be mostly described by rotation. So when we compute the molecular outflow rates and plot against the bolometric luminosities, here we see for the circles are the molecular detections, and the squares and triangles are the ionized ones. And we can see clearly that we are starting now to populate with the circles this region below this empirical relation that was mainly drawn by the most extreme cases. Now we are starting to detect fainter outflows. And for the ionized one, have a look at this work by Giovanna Speranza, that she used Megara observations to determine accurately mass outflow rates using the O3 line. But what about the driver source? So when we compute the energetics of these outflows, so here in the right panel, I show the kinetic power of the outflow against the bolometric luminosity. And we can see that there's a huge scatter in this relation. But when I try to compute the same kinetic energy against the jet power on the left, we see that this scatter is lower. So this might indicate that in this, the case of these quasars, these radio-quiet quasars, there's a combination of radio and quasar mode acting together. So we are going to have some new observations. So we were awarded 30 hours in cycle 2 with James Webb with the MRS. So we'll be able to trace the ionize, the warm molecular, and also the pHs to trace the nuclear, to infer the nuclear impact on star formation of these agents. And we were also recently awarded with cycle 11 with ALMA to study this line ratio in other 5 quasars that shows clearly jet-like morphologies. And we are going to complete all the sample using configuration A with VLA. So just to my takeaway message, so even though agent feedback is not really quenching the host deformation and depleting the gas molecular reservoirs in these galaxies, we find clear evidence that AGN feedback from these low power jets of these winds from the quasars are disturbing the morphology, also the kinematics, and in some cases as the star formation in the central kiloparsecs of this galaxy. So we are witnessing the impact of feedback in this the current episode of feedback on these galaxies. So if you want, have a look at this press release from the results on the teacup. Thank you very much.
Great, thank you very much. I think we have time for one or two questions if people have. I'm not supposed to walk by, so yeah.
Can you say a little bit more about the morphologies of the host galaxies in the QSO feed sample?
It's quite broad. We have some cases of spirals, some early type galaxies, mergers, post-mergers. So it's a bit of everything. It's a mix. In this sample, in the first SALMA proposal, we tried to get a little bit of every type of morphology. And actually, we observed 7 galaxies, and the 2 early type galaxies were not detected in CO. So only like the interacting systems and the spiral ones.
Thank you.
Okay, so I would say let's thank Alanis again. I think our next talk is online. Is that? No? Okay, I haven't.
Hello, can you hear me?
The speaker's online. Oh, but are we sharing the screen? Okay, perfect.
So should I share the screen?
Yes, please go ahead. And so I will, you can hear me okay?
Yes.
Okay, so I'll give you a warning at 2 minutes if that works.
Okay. Let me see desktop. Yeah. So hello everyone. Yes, my name is Bo, and I'm a postdoc at MPA. Sorry, I cannot present in person because of the delay in visa, but I will be in Cape Town from Friday, I think. Yes. And I will like slightly make a detour, go to higher frequency and talk about these fine structure lines. For a very, very brief introduction, these fine structure lines are the fine structure transitions on the ground state of these ions. They are typically have very low energy in the mid-infrared to far infrared bands, which results in very low attenuation, especially compared with optical lines. They also show very little dependence on the electron temperature. These lines are collisionally excited, making them good diagnostics of the physical conditions in the emitting gas. They are also major coolants in ISM, so they are bright. These lines come from a diverse collection of ion species and origins from basically all phases, from ionized to atomic and into molecular gas. I'm listing the fine infrared fine structure lines that I'm going to talk about, although I will skip the C1 line because they are more closely related to the molecular gas, while others are emitted from either ionized or atomic gas, which show very interesting behavior. These lines attracted significant attention in the past decade, especially in the high redshift universe, partly because they're bright. C+ and O388 lines, you may have heard of them. They have been used very widely for discovering and confirming high redshift galaxies, and they are often the only line that can be observed to study the ISM conditions in these galaxies before the launch of JWST. However, there are quite some problems in studying these lines. First, several gaps existed in the observations And the diagnostics of these lines were like calibrated in mostly low Z observations 20 years ago. But when we go to the higher redshift, despite large effort by the community, most of the data we have are still the unresolved integrated line fluxes, making it questionable whether these calibrations are still applicable or not. Other gaps include that many of these lines were detected or studied in the dusty massive galaxies, but whether we can also apply these calibrations on the low metallicity and low mass galaxies, which are like the majority of the very high, extremely high redshift galaxies we know. Yet another gap is between the fine infrared diagnostics, whether they can be directly compared with other gas tracers or not, especially the optical ones. Little studies have touched on this. On the theoretical part, there are also many challenges. I'm listing a collection of some papers talking about the C+ line, how people try to interpret it. And it looks like with different assumptions, people can relate this line to basically everything in the galaxy, from star formation to fine infrared field to atomic gas to molecular gas mass. So there is a strong lack of consensus in interpreting this very bright line, and it really bothered me. Many of these relations are probably just a result of the fundamental scaling relation of the galaxy, which is that bigger things are brighter. More questions exist in theory. For example, historically, neutral gas are studied in the framework of PDR, and ionized gas is studied in the framework of H2 regions, and only a few attempts trying to connect both phases. Also, the simulations or models trying to understand these lines require more observation data to calibrate them or verify them. So the approach I took was to not going to ARMA and get even more data, but go back and go to the literature. I collected basically all the published fine structure line detections that I can find in the published data, which results a big atlas of more than 1,000 galaxies in the local universe and more than 500 galaxies in the higher universe. And when assembling this catalog, I focused especially on correlating with multi-wavelength data, especially the mid-infrared and optical data. I also computed the photoionization model grid with 5 dimensions for a comparison of this big atlas of data. So with the time limit, I cannot show all the results because with so much data, there is a lot of things to explore, either old or new calibrations, but I'm going to just flash across some of the very interesting things. First, I'm showing you the demographics or the landscapes of the fine infrared studies so far. From just this infrared luminosity across redshift plot, you can see the strong bias of the fine infrared lines, fine structure line study. Basically, all the detections we have for high redshifts are on the lurks region. I'm showing many figures in this color scheme in this talk, so I will briefly explain it. The only important data points are red for infrared bright galaxies, either ULUX or the submillimeter galaxies in the high redshift. The blue data points are UV bright galaxies, either dwarf or Lyman brick galaxies. The blacks are Adrian hosting galaxies. The small data points are low Z, and the big data points are high Z. I can also show this for this fine structure line detections across redshift. C+ is still the best observed ones, followed by the O3, with the only exception of N+205, although N+205 have a problem with the biasing in the galaxy types observed. So first, one interesting thing is to see how much Adrian contribute to this line, because people didn't think any of them have Adrian contribution. The method I use is to use the very high ionization line, the mid-infrared neon 5 or oxygen 4, to trace the Adrian contribution when they are normalized by a common line. This shows an example that I can basically decompose the neon 3 and sulfur 4 into either star formation domination and Adrian domination, whether they are following the horizontal branch or a linear correlation branch. And this can be applied directly on the O3 and O1. And you can see in AGN hosting, non-AGN hosting galaxy, at very high line ratios, the O3 and O1 do show linear correlation with these very high ionization lines, showing clear AGN contribution to these lines. Another interesting topic is where is C+ from? This has been studied like for 20 years. The logic is very basic if you compare it to a line that's clearly from the ionized gas. Usually people use either N+ line, 122 or 205, and 205 is preferred. And people have suggested that dwarf galaxies have more C+ from the neutral gas compared with the rest of the sample, although these studies typically don't consider that nitrogen has a weird abundance pattern. And if you correct this nitrogen abundance, there will not be more systematic variation between this neutral fraction for C+. And N+ to C+ ratio is more like N2 ratio empirical diagnostics instead of the C+ neutral fraction. Yet another thing that I can do when I have optical data in hand is that with H alpha, the extinction corrected H alpha as a tracer of the full ionized gas mass, I can do basic elemental abundance with little dependence or worry about the electron temperature. This is showing different lines divided by the H alpha, the extinction corrected H alpha luminosity compared with metallicity. These dashed lines are not fit. They are the expected intense flux ratios using computed at typical gas conditions. And you can see they actually agree in a very surprising way. This means H alpha can be this normalization for metallicity measurement, and that despite whether it's from the neutral gas or from the ionized gas, like O3 or C+ or O1, there's insignificance of this phase difference, and both phase of gas behave in a very coherent way. Of the particular interest is the C+ to H alpha comparison. If you think extinction corrected H alpha is a measure of this golden standard of the staff emission rate measurement, this means C+ is correlated with the staff emission rate by a factor of metallicity. This also explains why when people try to use this line or try to calibrate this line for staff emission rate, they get different normalizations and different scatters using different samples, and they often get some slope trying to calibrate this thing. And more interesting thing is that if C+ can actually be used to measure staff emission rate, what is C+ deficit? This is a very old topic that can date back to more than 30 years ago. And it has this significance is that if infrared luminosity also means staff emission rate, but C+ is showing a deficit, which is in contrary to what I just showed, where is the common point here and why they are conflicting each other? So I would like to discuss this, and the answer is kind of surprising. So first, it has been realized before that it's not just C+ that's showing different deficit. Every fine structure line shows deficit. This is showing the line deficit of O3, O1, N3, and N+. Different lines show different extents of deficit depending on the coverage of these lines, but this going down trend appears at luminosity something like 3 times 10 to the 11th. And more interesting thing is that if you compare deficit to deficit, this is line to infrared ratio of all these lines with C+ to infrared ratio at the x-axis. These dashed lines have a slope of 1 separated by 1 dex. You can see almost every line show the same deficit trend, and some of the lines show even tighter deficit trend to C+ deficit, especially the O1 and N+ lines. This immediately rang the alarm for me that this common quote deficit trend are the result of a problematic denominator, which is the infrared luminosity. It's not just far infrared. The H alpha, the extinction corrected H alpha, also show this line deficit. This is showing H alpha over infrared luminosity as a function of infrared luminosity or the C+ deficit. You can see in infrared bright galaxies that this line, the H alpha, is also deficit, and this deficit is about 1-to-1 to C plus if we ignore the dwarf galaxies, which has a more complicated dependence on the metallicity. This is in stark contrast to what we have believed in so many years. In this famous Connecticut 2009, it is believed that the infrared luminosity has been calibrated as the standard for the star formation rate based on the H alpha extinction corrected H alpha. But what people have not realized for enough importance is that this paper has sample selection in its spectroscopic sample. Sorry. Yep, it actually exclude all the galaxies with not enough signal-to-noise ratio of H beta, and this effectively exclude most of the infrared luminous galaxies. If I don't do this exclusion and remake this figure, instead of a 1-to-1 relation, the nice relation shown in the original paper, you can see this big scatter if you include all the spectroscopic data without any cut. And this scatter is not because of the concern of extinction. This data will have the exact correspondence with the far infrared lines, including O3, sorry, not O3, but C plus and O1, which means they are much smaller than the infrared luminosity because of some intrinsic reason that infrared luminosity is doing something weird. And at the very least, it's good to remember that the dusty galaxies are practically not calibrated in this Connecticut 2009 relation. And what is dust doing is still not clear, but this trend in dust property is also leaves an imprint in other property, other scalings of dust. As a function of metallicity, from low metallicity to high metallicity, or from the low dust to gas ratio to the high dust to gas ratio, the dust behaves in a very ordinary way. This it takes a steadily higher fraction of the energy from like ionizing photon.
Wrap up in about 1 or 2 minutes.
Yes, yes. It's less than 2 minutes. And you can see this trend of dust temperature decreasing and infrared excess increasing. However, in high enough at metallicity minus 3.5 for infrared luminosity 10 to the 11th, all these nice relations starts to break and infrared luminosity starts to increase without correlation with any of the gas property. This is very difficult to explain in the conventional picture of ISM because dust emission would be in the downstream of the energy flow. To create this very large infrared luminosity without changing the line luminosity, you need either extra energy source for dust like non-ionizing photons or non-radiative heating for dust, or you need to create intrinsic ionized gas deficit by moving dust emission upstream. Either that there's a lot of dust in H2 region that's emitting this extra energy, or that H2 regions are so leaky that the leaking ionizing photon directly plant the dust and heat them. I will skip this part. And because of the time constraint, I cannot show all these interesting results. And but the catalog and the paper will be submitted soon, and the catalog and the photoionization grid will be also public along with the papers. I will leave the summary here, and I would like to take any question.
Thanks very much. I think we have time for 1 or 2 questions. Just one top up.
Hi, Bo. Thank you for the talk. So you were presenting the plots using the H alpha corrected for extinction, but I mean it's very good. It's very difficult to do a good correction.
Yes.
When you have a lot of extinction. Fundamentally, it doesn't matter that you detect some H beta. It's not. You cannot correct for things that you don't see. No. So how certain are you that this is going to work? I mean, this will break down essentially for the brighter sources, very likely.
Yeah, I'm not saying this extinction correct is precise. However, the matching with the Frankfurt line tells you they are probably order of magnitude correct, and and the big deficit is due to other effects. So this is going to create quite some errors that cannot be measured, but that will not be the dominant source of uncertainty.
Okay. Other questions? If not, look for Bo on, you said Friday you'll be here?
Yes.
Let's thank him again. We will come to the last talk of the session. So I'm happy to give you a warning, but honestly, since the last talk has been canceled, just do your best and stay roughly on time, and you have plenty of time. So please take it away.
Okay, thank you. Can you all hear me? Okay, thank you very much. So my name is Mavis Seidu, and I'm going to talk about meerkat detection of low surface brightness H2 regions associated with highly variable 6.7 gigahertz methanol mazes. So in the
the green button should move
forward.
No. And then,
I want to use the pointer. Okay. Okay, so in the Milky Way galaxy, there are about 100 billion stars that are formed in the Milky Way galaxy. And the massive stars are known to be few but highly energetic stars in the Milky Way galaxy. So by massive stars, we mean stars with masses greater than 8 solar masses, or solar mass, yeah. The formation of these massive stars occurs inside dark, dense molecular clouds. So for example, the image above is a molecular cloud, and the massive stars, once they are formed, they produce high amounts of UV radiation with which they ionize hydrogen in their environment. So this creates what we call H2 regions. The H2 regions have various morphologies. The most compact ones are known to be bright, and they are easily detected in radio wavelength. Because the massive stars are highly embedded sources, one of the easiest ways to study their physical properties is to use the emission of masers. So maser is an acronym for microwave amplification by stimulated emission of radiation. So the diagram below shows the evolutionary stages of masers when they form in massive star forming regions. And there are different types of masers. We have the methanol maser, OH maser, water maser. And the methanol maser, there are different classes, but the class 2 6.7 gigahertz methanol maser is known to be one of the brightest masers we can find in massive star forming regions. So now the total sensors of methanol masers that have been detected in the Milky Way galaxy stands at 1,085. And the highest of these surveys have been done using the methanol multi-beam survey. One thing I also want to indicate is most of the time, the 6.7 gigahertz methanol masers are usually formed because they are signatures of early formation of massive stars. So once the ultra-compact H2, once an H2 region is formed, or a compact H2 region is formed, they provide the seed photons for amplifying these masers. Since I have all the time, please bear with me. So there have been a number of surveys to search for these H2 regions in massive star forming sites. So a number of these searches have been carried out, for example, that of Walsh 1998 and Hu et al. 2016. So for example, that of Welsh 1998, he found out of 233 methanol meso sites, only 46 of them were shown to have ultra-compact H2 regions, with the remaining having no radio counterparts or radio ultra-compact H2 regions. So these are examples of surveys that I have, sorry. So in the box are examples of surveys that have been carried out to search for these radio continuum counterparts associated with 6.7 gigahertz methanol mesas. And one thing I would want you to take note of is the sensitivity limits of these surveys. So the question comes in, why is there non-detection in these methanol meso sites? Could it be because of sensitivity of previous surveys, the telescope that was used by previous surveys, or is it that the sources are so young that the H2 region is not formed yet to be able to kind of amplify these mesas in these regions? So in this talk, I'm going to show you how we use Meerkat, which is 4 times the sensitivity of, for example, that of Hu et al., which used VLA configuration C for their work. And what is also interesting is that Meerkat is used to do galactic surveys. And one of the examples of the Meerkat galactic survey is that of the SMGPS, which is the observation was done in 2018 to 2020. So the number of pointings, we have about 1,046 pointings, and the observation is done along the plane of the galactic, the Milky Way galaxy, where most massive stars are known to form. So out of the 1,085 methanol mesas, a lot of work have been done to find the properties of these mesas, and some are known to show characteristics of variability. So when we say variability, is how the flux density is changing with respect to time. So in 2002, Budat et al. Did a long monitoring of 59 methanol mesa sites. And for the first time, she discovered 7 of these sources to show periodic variability. So currently, there are 32 of these mesa sources to show this periodic behavior. I hope I'm not too loud. I'm okay. Okay, thank you. And out of the 32, only 21 of these sources have been found to have associated ultra-compact H2 regions. And that contributes to the 66% of the pie chart on the left. 11 of these sources are found to have no ultra-compact H2 regions. And this is very interesting. So with Meerkat, this is the table of all the 11 sources. And with Meerkat, I searched for radio continuum counterparts of these sources. Unfortunately, 3 of the sources were not detectable due to the declination that we see on the table. So those are indicated as red, but the remaining 8 are observable with Meerkat. So we found out of the 8, only 4 of these sources are having radio continuum counterparts. And so statistically, this is how I represent these sources. So 50% detection and then 50% non-detection. So in a few couple of minutes, I'm going to show you examples of these sources. And so the first example is source G45.473. This is a periodic methanol mesa source. And with Meerkat, so the position on the left is the Meerkat image of the source. And the position of the 6.7 gigahertz methanol mesa is indicated with the blue cross. So we can see that there is a faint emission around that position of the methanol mesa. A second example of another source is G328.24. So this source is also known to be a periodic methanol mesa site. And with Meerkat, we even find multiple components in the field. Lastly, I'm just going to show you an example of a non-detection. So this source, which is G339.989, is not detectable because the upper limit, the upper limit of this source is around 3 microjansky, and it's below the sensitivity of MECAT, which is 10 microjansky. So we were not able to detect any radio continuum at the position of the methanol maser. With the upcoming detection of new periodic methanol masers, this is an example of a new periodic methanol maser site that was reported by Nell et al. In 2023. And this source is known to be a radio quiet source, according to Anderson 2014. And with MEERKAT, we found a radio continuum at the position of the methanol maser. This is also an example from Hu et al., who used the VLA configuration C to also find ultra-compact H2 regions. And we can see so the image on the left with the cross is supposed to be the position of the methanol maser. So with MEERKAT, we can see a very faint, good coincidence of a radio continuum associated with 6.7 gigahertz methanol maser, and that's where I've indicated as red cross on the right image. So these are very interesting, and it's very interesting that with MEERKAT, we can be able to actually find radio continuum associated with such sources. So in summary, I have conducted a search for radio continuum counterparts of 11 methanol maser sites, which were previously known to have no ultra-compact H2 regions. Out of the 11, only 8 were observable with MEERKAT, and even out of the 8, 4 of these sources were found to have radio continuum counterparts. So with the upcoming SKA, this will be very advantageous to detecting even faint sources in star-forming regions, such as the ones that I have shown. So if it is in terms of sensitivity, with the SKA, we can be able to actually find more of these sources. It's also possible that some of these sources are so young that the ultra-compact H2 region may not have been formed. So those ones, we still have to find the way to explain the mechanism that is responsible for the maser emission that is happening in such regions. Thank you.
Thank you very much for the nice talk. We definitely have time for questions if folks have them. Yeah, please.
Hi, thank you for your talk. The variability that you mentioned, do you know what exactly is the process creating this variability?
Okay, so for the variability that have been reported, there are different mechanisms that have been proposed. So for example, one of it says that once a radio continuum or ultra-compact H2 region is formed, the changes in the variation can cause the changes that we see in this maser. So it can affect the properties that we see in this maser. So such study is very important to really be able to model these properties very well. But if we don't find more of these sources, they are very constrained.
Other questions? So I would, maybe a quick question. So are the non-detected sources also fainter in Atlas Gal? So is the infrared in the background also fainter?
No, so, sorry. You see the gray contours at Atlas Gal. So the Atlas Gal is very, yeah. Okay. So it's highly,
so it's really all over the map.
Yeah.
Neat.
Please ask questions.
Mavis, have you checked at higher frequencies for detections?
Okay, so I haven't really checked high frequencies, but for some, let me say, I checked the ALMA observations of some of these sources, and yeah, so that's the only one I have used, but not any other. high frequencies.
All right. I think folks are coming to the end here and look a little tired, so let's thank all of the speakers again. I would suggest we also thank Alberto, Ava, and Nami, and the technical staff have been helping us out for the few days too.
Yeah, thank you. Thank you guys for running the presentations. That has worked very well. Thank you. I would like to ask for a round of applause, not just for the speakers, but also for the poster presenters. I wish I had more time to actually run downstairs and look at all the posters and all that. But you guys were part of the meeting, and you deserve a round of applause too. I think we are intending to collect the presentations. There is a small matter of the proceedings. We're trying to negotiate the proceedings part. So we'll send around an email, and we'll try to collect the presentations from everybody, not just the talks, but also the posters, to put in the website. So expect that email. And I guess I have to ask for a round of applause to our chairs who actually kept us on time, so that we have been running pretty smoothly throughout.
The final words?
Yeah, of course, always.
To the chair of the SOC, who was working tirelessly to keep things on track and answering a lot of emails that came from the organizations, and also for putting together this awesome program.
And I think this is it. You're free. Sadly, we had a few cancellations. That's okay. It happens. And I'll see you throughout this week and the next. Thank you.
Looks like we have a lot of videos. This is PowerPoint, one video, 2, 3.
Yeah, well, the recording, this is the recordings. What is this called?
Keep music. So now I've been dropping slowly so they can feel like we wanna focus.
Huh? Jong, wat dat gewoon een treintje. Ik denk dat ik zit er zo. No?
Until the room is done, then.
Yeah, you can stop the recording. Stop on Zoom. Yes.
Is that okay?
There's nothing in coming. Yeah.
Okay.
Session is over.
Session over.
What do you want to wait for?
Nobody.
One more work. Okay.
Nobody.
You can go to only one. They're running okay.
Excuse what?
Yeah.